So that will make it better. So, okay. I was in another meeting, so got mixed up. Hello.
Sir, we'll proceed, sir.
Yes, please.
Okay, sir.
So this is on course is online.
Yes, sir.
Okay.
Yes, sir. Online, sir.
Okay. Okay.
You are visible and audible, sir. We'll proceed,
Okay.
sir.
Okay.
Thank you.
A very good evening to one and all. With immense pleasure and pride, I, Dr. S. Reddy Kasim, Associate Professor, Department of EEE, Vishnu Institute of Technology, Bhimavaram, take this privilege to warmly welcome you all to the inaugural function of our one-week online Atal Faculty Development Program on emerging trends and future prospects in advanced energy conversion technologies and applications, which is organized by the Department of EEE, Vishnu Institute of Technology, and sponsored by the AICTE Training and Learning, Atal Academy, New Delhi. We are truly honored to have amidst our chief guest, Professor Dr. Mukesh Kumar Pathak, Professor, Department of Electrical Engineering, IIT Roorkee, a distinguished academician and a learning expert in powertronics and electric vehicle systems. On behalf of the organizing committee, I extend my heartfelt welcome to the management of Sri Vishnu Education Society for their continuous encouragement and commitment to excellence in education and innovation. I extend a warm welcome to our principal, Dr. M. Venu sir, whose leadership and guidance inspire us to scale new academic heights, and our vice principal, Professor M. Srilakshmi madam, for her constant support and motivation. The respected deans, heads of various departments, and faculty members of Vishnu Institute of Technology, and all the participants from across India, faculty, research scholars, and industry professionals who have joined us to make this FDP a grand success. Together, we all unitedly begin a week-long journey of knowledge sharing, learning, and exploration into the dynamic field of advanced energy conversion technologies. Let's begin this auspicious occasion by invoking the blessings of the Almighty. I request everyone to join for the digital lamping ceremony.
कुरुत्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः
So thank you for that soulful rendition. Now, to give everyone a glimpse of the vibrant atmosphere and innovation-driven culture at our institution, let us watch a short Vishnu Campus Bhimavaram video showcasing the excellence and facilities of our Vishnu family. I request Professor Naveen, sir. Thank you. That truly reflects the vision and spirit of our institution. So now, to extend a warm welcome and set the tone for this FDP, I now invite Dr. R.V.D. Ramarao sir, Professor and Head of the Department of EEE and Coordinator of this FDP to deliver the welcome address. Thank you. Over to you, sir.
Good evening and warm greetings to everyone. Respected Chief Guest, Dr. Mukesh Kumar Pathak, Professor, Department of Electrical Engineering, IIT Roorkee, Principal Sir, Vice Principal Madam, Deans, Head of various departments, resource persons, participants, and dear colleagues. It gives me great pleasure to welcome you all to this online AICT Atal Faculty Development Program on Emerging Trends and Future Prospects in Advanced Energy Conversion Technologies and Applications, organized by the Department of Electrical and Electronics Engineering, Vishnu Institute of Technology, Bhimavaram, from 10th to 15th of November 2025. This FDP focuses on one of the most dynamic and essential areas of modern engineering, like advanced energy conversion technologies. It provides an excellent platform for faculty members and researchers to exchange ideas, explore innovations, and discuss future prospects in the crucial field. I make this opportunity to express my sincere gratitude to our Principal Sir, Vice Principal Madam, and the management for their continuous support and encouragement in organizing such academic initiatives. I also extend my thanks to AICT and Atal Academy for their continued efforts in promoting quality faculty development programs across the nation. My heartfelt thanks to our esteemed resource persons from reputed national institutions for sharing their valuable knowledge and expertise and for accepting our invitation despite their busy schedules. I also appreciate the sincere efforts of our FDP coordinators and organizing team for their dedication and meticulous planning in making this event possible. To all the participants joining from various institutions, I extend a very warm welcome and encourage you to engage actively, learn wholeheartedly, interact freely, and make the best use of this academic platform. Once again, I warmly welcome you all and wish this FDP a grand success. Thank you all.
Thank you very much, sir, for your motivating words and for setting the direction of this week-long journey, FDP. It's now time to hear from the leader who constantly inspires the VIT Bhimavaram with his guidance and academic excellence. I invite our beloved principal, Dr. M. Venu, sir, to deliver the presidential address.
Good evening, one and all. Respected today's chief guest, Mukesh Pathak from IIT Roorkee, and all other participants from various regions of India. So warm welcome to all of you today. The Vishnu Institute of Technology established in the year 2008 with 4 branches of engineering, having experience of getting experience of 17 years of age of VIT, reached a height that we are the ranked 3 among all private engineering colleges in the state of Andhra Pradesh, and having the laurels of NBA, NAC, and other accreditation status also. And being a campus of Vishnu, Sri Vishnu Education Society, which is led by our visionary chairman, K.V. Vishnu Raja Garu, followed by vice chairman, Sri Ravichandran Rajagopal Garu. So who is a visionary management, having educationalist as well as industrialist. So leading our institutions throughout Andhra Pradesh and Telangana, top 10 rankings in all endeavors. At the same time, apart from the academic excellence, we are also actively participating in all kinds of hackathons and Smart India hackathons and TIGRAD. Especially the Department of EEE is winning a lot of laurels and prizes and having projects from DST and other bodies also. So coming to the today's important FDP inauguration. So that is on emerging trends and future prospects in advanced energy conversion technologies and applications. So now why people are looking for energy conversion technologies? So because everybody knows that the prices of fuel is increasing. That too, we may not be able to get the fuel in near future. So that is why people are looking for alternative energy sources. So with that, so all the researchers are doing their best, and so innovative way only they are doing a lot of things. So coming to our institute, so we are having the alternative energy solutions lab and especially the battery lab, and our faculty and students are actively participating in Baha competition, and our students and faculty manufacturing the all-terrain vehicles and how to reduce the fuel consumption. So with research and innovative things, our students and faculty both are working hard to get lot of new technologies by the students and the faculty members. So I hope this 1 week FDP definitely enlighten you on various fossil fuels and alternative energy solutions. Will give you a lot of inputs, because the resource persons from various academia as well as industry, so definitely they will share their knowledge and transfer their knowledge to all of you, all the participants. So I request all the participants, so even though it is an online program, please meticulously attend all the sessions and make use of this 1 week FDP and transfer your knowledge to your students, so that as a whole, your institutions as well as the India will enlighten with this the advanced faculty development program. With this, I wish you all the best for all the participants. Thank you very much.
Thank you, sir. Thank you very much for your valuable insights and observations. To grace the event with her inspiring thoughts, I invite Professor N. Srilakshmi Bhatta, Vice Chancellor of VIT Bhimavaram, to deliver the presentation. Over to you, Madam.
Thank you, First Lady, sir. Good evening to all. First of all, my heartfelt thanks and welcome to Dr. Mukesh, sir, Professor IIT Roorkee, accepting our invitation as a chief guest. Thank you so much, sir. And I want to appreciate the coordinators of this is Atal FDP, Dr. Ramarao sir and Dr. Kazi Reddy sir. Sir, in order to come to the EEE department, our Vision Institute of Technology started in 2008, and the EEE department is there in the college from the 2008 onwards, and department has won so many laurels as mentioned by our principal sir, and the department is consistently accredited by NBA from 2014 onwards, and now we are the autonomous college. And as your topic, today's topic, FDP topic is mainly on the advanced energy conversion technologies. So we have a lot of importance in the EEE department in our college, and we are happy to share you that we have an alternative energy solutions center of excellence in our college. So the projects which are developed in that center of excellence has won so many competitions, and in order to make emphasis for these alternative energy solutions, we have nearly 0.5 megawatt solar power panels embedded installed on all the rooftops of our buildings. And majority of the power generated from our solar panels is only utilized in the college. And sometimes we are giving that power back to the grid also. So, and we are taking so many measures in the campus to make use of alternative energy solutions. And definitely this FDP will give more emphasis on the related topics, advanced topics of these alternative energy solution conversions. And I hope all the participants will make utilize of this FDP. And thank you all for participating. Thank you once again.
Thank you. Thank you very much for your kind words and continuous support. Now it's time to introduce our distinguished chief guest for this inaugural event. To formally introduce Professor Dr. Mukesh Kumar Pathak, Professor, Department of Electrical Engineering, IIT Roorkee. I invite Professor P. Naveen, Associate Professor, Department of EEE, Vision Institute of Technology, to kindly take over and introduce our chief guest to the gathering.
Thank you, Dr. Kasim sir. Good evening to one and all. It is my privilege and honor to welcome our distinguished chief guest and keynote speaker for the inaugural session of our faculty development program, Dr. Mukesh Kumar Pathak. Dr. Pathak is a professor in the Department of Electrical Engineering at the Indian Institute of Technology, Roorkee. He earned his PhD in electrical engineering from IIT Delhi and holds an MTech in power electronics, electrical machines and drives, as well as a BE in electrical engineering. With over 3 decades of exemplary teaching and research experience, Dr. Pathak stands as one of the India's foremost experts in power electronics, electric vehicle systems, advanced motor drives, solar PV integration, and smart grids. Dr. Pathak's pioneering contributions include leading high-impact R&D projects funded by premier agencies such as DST, Imprint, Mission Innovation, and NHS RCL in collaboration with industry partners. He has been instrumental in developing silicon carbide-based solid-state transformers, megawatt-scale solar integration, and high-speed railway power modules. As an acclaimed scholar, he has authored the widely used textbook Electrical Machines and published more than 100 impactful research papers in reputed journals like IEEE Transactions and IETE Journal of Research. Dr. Pathak is a senior member of IEEE, a fellow of the Institute of Engineers, and has served the academic community in numerous leadership roles, including Chairman, Recruitment Examination Cell, and Associate Dean, Infrastructure, Electrical and Allied Circuits at IIT Roorkee. We are indeed privileged to have Dr. Pathak with us today, and we look forward to his insights on the future of sustainable energy systems, e-mobility, and smart grid innovations. I would like to thank the organizing team for giving me this opportunity to introduce such an eminent personality. It's truly an honor, sir.
Thank you, Professor Naveen, for the wonderful introduction. Now I request our honorable chief guest, Professor Dr. Mukesh Kumar Pathak, sir, to kindly address the gathering. Over to you, sir.
Okay, can you hear me?
Yeah.
Yes.
Okay, thank you very much for calling me to the inauguration of this program on emerging trends and future prospects in advanced energy conversion technologies and applications. In fact, this is a topic of very high, immense importance to the electrical engineers these days, because a lot of things are changing now. The energy generation patterns, energy consumption patterns are changing, and we are looking at the future with a system where the availability of energy is 24/7, and this energy should come from renewable energy sources. And as I can understand, or as I have heard from the speakers, from I think your principal, or I think vice principal, that you already have a solar power plant in your campus, which is 500 kilowatt capacity.
Yes.
And
Yes, sir.
you are you are contributing to the grid also. I think
sir.
this is the change that has come in our system, in our thought process for last 10-15 years. Earlier, we used to think about power generation only for experimental showcasing. But now we are not only generating solar power for our own use, but also supplying it to the grid. And as the things stand today, India is one of the is becoming one of the leaders in renewable power generation. We have large amount of solar power which can be converted into electricity. We have hydro potential, we have wind potential. So all in all, we have everything that renewable power generation requires. What we need to do further is to accelerate this development, and also see how this our grid is made capable of absorbing this. So I think this course will address a lot of issues regarding electrical conversion system, different types of renewable energy systems, and what recent developments are. What are the recent developments going on in that area? It will also, I hope that speakers will also enlighten the participants on both broad aspects of these generation systems, and also the minute details about the generation and the advanced power energy conversion systems. I hope that this course will provide a lot of good material and good learning effort to the participants, and they'll further disseminate this this learning to their students and the community at large. I am once again thankful to the principal of VIT, vice principal, and the coordinator of the course, Dr. Ramarao, for inviting me to be the chief guest in this inauguration. And I wish you all a good time ahead, all participants, good time ahead, and wish the Institute, VIT, success in organizing this course. Thank you very much.
Thank you.
So much.
Thank you, sir.
It's our pleasure to have such an eminent person as a chief guest today.
I think it's I'm also thankful to you for inviting me and giving me a chance to speak to your audience and your faculty members.
Thank you, sir.
Thank you, sir.
Thank you so much, sir, for your enlightening and motivating inaugural address. Your words have truly inspired us and set a great tone for this faculty development program. Now, every successful event requires the effort and cooperation of many hands. To express our heartfelt gratitude, I invite Dr. I. Kasireddy, co-coordinator of this FDP, and he is an associate professor in the Department of EEE VIT Bhimavaram, to deliver the vote of thanks for the inaugural session.
So good evening, everyone. So I am Dr. I. Reddy, coordinator of Atal FDP. It gives me an immense pleasure to deliver the vote of thanks for this inaugural session of our Atal FDP on emerging trends and future prospects in advanced energy conversion technologies and applications, organized by the Department of EEE VIT Bhimavaram. Firstly, I extend my heartfelt gratitude to our management, principal sir, vice principal madam, deans, and heads of various departments for their constant support and encouragement. A special thanks to our chief guest, Professor Mukesh Kumar sir from IIT Roorkee, for sharing his valuable insights and setting the right tone for this FDP. We also deeply thankful to the AICT Training and Learning Academy for sponsoring and supporting this program. My sincere appreciation to the organizing committee members for their dedicated efforts in making this event a success. To all distinguished speakers and resource persons from reputed institutions like IIT Roorkee, IIT Dhanbad, NIT Warangal, NIT Allahabad, CEA New Delhi, PDSL, and ORF America, we extend our gratitude for accepting our invitation and agreeing to share their expertise during the upcoming sessions. Finally, I thank all the participants for joining us and showing keen interest. Let us make the upcoming sessions truly enriching and memorable. So thank you all.
Thank you, sir, for your gratitude-filled words. With this, we conclude the inaugural ceremony of our Atal FDP. Once again, we thank our esteemed chief guests, dignitaries, coordinators, and all participants for joining us. We now move on to session 1, which is scheduled from 6:30 p.m. to 8 p.m. So on the topic solid state transformer for green energy, which will be delivered by our today's chief guest, Professor Mukesh Kumar Pathak sir. The session will be starting with a short break of 5 minutes. We request the participants to let's stay connected and continue this insightful journey on advanced energy technologies. Thank you all. And also, we request the participants to please switch on your camera so that we'll take a photograph. We request all the participants. Yeah, all the participants are requested to switch on your camera. Together.
16 or 25 first gallery 6 gallery తర్వాత
Max gallery better.
front page large gallery. Yes.
Thank you very much. We request the remaining participants also to please switch on your camera so that we'll have a photograph.
Screenshots. కింద ఇంకోటి ఉన్నట్టు
Three times good.
just multiple
Video
recording
Video recording.
Okay, thank you very much for all the participants. Now, the session will be starting within less than 5 minutes. I request the participants to please stay connected and request the chief guest, sir, within 5 minutes, we'll have a short break for the 5 minutes, sir, and we'll be having a session less than 5 minutes. We again welcome you all to the FDP. The request of Chief Guest, Professor Mukesh Kumar sir. Sir, can we start, sir?
Yes, yes, I'll share my screen.
Okay. Sure, sir.
Okay, can you see my screen?
Yes, sir. Yes, sir. It is visible, sir. You can go ahead, sir.
Okay. Okay, let
Thank
me
you.
also see if it is changing. Now, slides, next slide.
Yes, sir. Yes, sir. It
Next
is
slide.
changing, sir.
Okay,
Yes, sir.
okay. Okay, so welcome to this presentation on solid state transformer for green energy. This, as I discussed earlier also in the inaugural speech, that India is moving fast towards renewable energy generation. So we have already surpassed a target of 100 gigawatt of renewable energy generation, which excludes large hydro. So this is primarily this solar plus wind plus small amount of biomass and other things. As things stand today, India is fourth position in the world in terms of renewable energy generation capacity, installed capacity, and we are at fifth position in solar energy and fourth position in wind. And things are changing very fast. We are another 50 gigawatt of generation is under installation, and 25 or 27 gigawatt is in the process. So within few years, in a period of 1 or 2 years, we'll have another 75 gigawatt addition, making it nearly 200 gigawatt. And we are we are moving towards 450 gigawatt generation capacity by 2030, which still is 5 years. So that means every year we need to add at least 60, 70, 80 gigawatt capacity, renewable energy generation capacity. Now, when we are moving so fast towards renewable energy generation, it is now the systems are most of the systems are connected to the grid. So we have a lot of this 200 or 100 gigawatt renewable which is connected to the grid is now the grid which is initially not designed for renewables energy penetration of such a large scale. What impact it will have on the grid? The first and foremost impact is on the power quality. The power which gets evacuated from the renewable energy sources is delivered through power electronic systems, and power electronic systems by default they have their own limitation in the form of introducing harmonics. So the quality of power of the power which is injected into the grid is not pure sinusoidal, it's not pure form. So it has got a certain harmonics, and these harmonics they will grow up as the amount of renewable integration also grow up. Then there is a requirement of battery energy storage system also, because when you have such a large amount of renewable energy integration, these renewable energy sources are highly intermittent, and this intermittency of these sources need to be neutralized or to some extent leveled by using energy storage system, battery energy storage system. Again, when you have battery energy storage system, these are also connected to the grid through power converters. Again, the issue of power quality would arise with these also. And then you have a important issue of stability, because if you integrate large amount of renewable energy into the grid, how will it impact the stability of overall stability of the system, and what control measures should be taken to make the system more robust. So one of the solution, one of the part, one of the system which can be introduced into the into existing power system is a solid state transformer, because solid state transformer is a solution which can replace the existing power transformers or distribution transformers, and also provide a direct way of integration of renewable sources with the grid. So my presentation will, I'll try to cover some of these aspects in my presentation. Green energy and solid state transformer. Then this another aspect is which is being widely researched and which is gaining importance, is use of wide band gap devices for renewable power converters. These are the devices which are stand out differently as compared to SI devices, silicon devices, and they have got certain advantages and certain features which are seen as favorable for renewable power generation. Then we'll discuss how SST, solid state transformer architecture, can be tailored for. Hello? Hello? Hello?
Yes, sir. Yes, sir.
Okay.
Yes, sir. You're audible, sir. Yes, sir.
I think
Yes,
these are the your participants are the students and faculty members of electrical.
Faculty members. Faculty, sir. Sir, all are faculty members, sir.
Okay. Okay.
The qualification of affected PhD, sir.
Okay. So we'll also discuss prototype of solid state transformers which we have developed in IIT Roorkee, and I think with this that would be too much for today. And we have high frequency transformer design, also a few slides on that, and how to scale up these converter topologies, SST topologies, for more and more green energy deployment. So, role of SST. Now, renewable energy integration essentially means integration of solar and wind. And SST has a role in both of them. It is also, poised to play a vital role in EV systems for fast charging. It is also, important to understand that smart grid system will also have the solid state transformer, and decentralized distributed generation system will also require transformers which are controlling. So solid state transformer is different from a conventional transformer in the sense that it is a transformer which has got many controllable features as compared to conventional low frequency transformers. So if you see the figure, this is a low frequency transformer, this is also a low frequency transformer. And solid state transformer, on the other hand, will come with lot of power electronics and high frequency transformer. It can also find applications in traction system, because in train also, when you charge the, when you get energy from the overhead line, this is 25 kV line, and the system inside train doesn't operate at such a high voltage. So you require a transformer inside the locomotive also. So that transformer uses a conventional low frequency transformer, but the problem with that is that this transformer becomes very heavy or very bulky in size. So if we can replace it with solid state transformer, lot of space, lot of weight will be reduced, and the locomotive will become lighter as compared to conventional one. And then we will also have we are also moving into a situation where the battery energy storage systems are also being installed. And this battery energy storage system will also require some kind of voltage transformation. So solid state transformer can again play an important role in this one. So the next question is, what is the, we'll limit this to solid state transformer first to only distribution system, because the first penetration, that is solid state transformer, if it has to penetrate into the system, it would be the distribution transformer, replacement of distribution transformer. Distribution transformer means the transformer at the back and at the last point of the consumer. So typically the transformers are pole mounted, they look like this, or sometimes a smaller transformer like this. The distribution transformer as such, it is a highly robust and reliable system. We know that the transformer's failure rate is very low, and we almost get electricity from these transformers even if we overload them. So they have got a lot of capability of overloading also, and they have very high efficiency. Efficiency of these transformers is sometimes more than 99%, and that makes them these transformers, they become they can handle large power because efficiency is large, so we can afford increasing the size of transformer without really bothering about the loss dissipation. So the transformer sizes they come in hundreds of megawatt of sizes, and this is primarily because of the high efficiency. And the efficiency of this transformer grow as the size grows. And they are relatively inexpensive because the transformer cost may run into crores, but that would be the case when the transformer rating is megawatt. But if it is in kilowatt, the cost would be only few lakhs. But all these years, even though we have been using the conventional distribution transformer, we are still using them. But we have been, we have been experiencing certain limitations. There is no, the control over voltage or frequency is not there. Voltage control is there to some extent because on-load cap changing can do that, but that feature gives us only limited voltage control. If the voltage falls drastically or increases very rapidly, in that case, these transformers would not be, helpful. They will either supply at very low voltage or will have very high voltage. Both cases, both the things are dangerous because high voltages can damage the equipment and the transformer itself. Low voltages can lead to unacceptable, operation of the loads. That is also harmful. And the other thing is that these transformers you cannot control the power flow in this transformer. That is, the power flow route is conventional. It is from input side to the output side. If you have a load which is capable of generating, these transformers cannot adapt to that situation at their own until the load voltage is increased beyond the point of the output voltage. Now, these transformers, the third point is that there is no DC port connectivity. You cannot either connect a DC source to the transformer or get a DC output from transformer directly. So DC port connectivity is not there. Now, with the penetration of renewable energy generation and also the penetration of lot of non-linear loads, even the lighting loads, even the IT loads, computers, these are the loads which finally consume the electricity in the form of DC supply. So that DC is actually obtained from conversion. So you have an additional conversion stage. And this system is, the conversion of power from one type to another type becomes essential in such cases. And even though we are taking power from the transformer, but we should be mindful that the additional conversion from AC to DC and then DC to AC, that should also be factored in. That is also something which is required. With with this conventional transformer, the overall structure of renewable power integration, renewable source integration becomes complex. And this transformer, you can see the transformer size has not reduced over the years. We continue to see these transformers which are very, very, bulky, very large weight, and they cannot be transported, they cannot be handled without special measures. You can see that the transformer that we used to see 50 years back and the transformer that we now see of same rating at today, the difference in the size, design, or weight, the change is very small. It's not a big development. It is not a change which can which could have made the life easier. So it's only say about 80% reduction, primarily driven by the improvement in the material. But the transformer which weighs 10 ton now weighs about 9 ton. So that it is not even though there is a reduction, but this is not such a dramatic reduction that it can be counted as something which will be revolutionize the use and installation and application of transformers. So major issue is that you do not have, its weight is very large and volume, it occupies large volume, do not have DC port connectivity and no control of voltage and frequency. The solid state transformer, on the other hand, what it can do is, it is a transformer which has which will look like this. You have a source, conventional source, AC power source, then a power conversion stage, followed by a transformer. Now this is a transformer which operates at very high frequency. In conventional transformer, the transformer link operates at 50 Hertz. This is a transformer which operates at very high frequency of the tune of few kilohertz, 5 kilohertz, 10 kilohertz, 20 kilohertz. So the transformation link or the transformer link between this side, input side and output side, is a high frequency transformer. And then you have, because this is a high frequency, you want to get back to the same frequency. So we will have a converter here, and finally 50 Hertz output. So 50 Hertz input here and 50 Hertz output. The difference is this would be higher voltage, typically 11 kV, 50 Hertz, and this could be 440 volt, 50 Hertz. So the transformation here is from this side to this side is a transformation, even though it looks as a transformation of voltage only, but it is voltage transformation accompanied by frequency change also. There is a increase in frequency, then a decrease in frequency. So solid state transformer will do both things. It will have two variables of control. One is the voltage, other is the frequency. So this high frequency, as we understand that when the frequency of transformer will go up, the core size will go down. And if the frequency becomes 10 times, well, we know increases by 10, a factor of 10, the core size could also decrease by a factor of 10. And in fact, any power transformer, the weight of that transformer is primarily contribution of the core. Even though copper windings will also have a contribution, but the more than 50% of the this contribution of weight is due to core. So that core, if it is reduced by a factor of, suppose if you have a transformer of 500 kg overall weight and 300 kg is the core weight and 200 kg is the rest of things, and if you can change this 300 kg to about say 50 kg or so, you have already reduced the transformer size by 1/2. And in fact, we can see that by changing the frequency, by increasing it further and further, a transformer of 1000 kg can become a transformer of some 100 kg. And transporting a 100 kg thing as compared to a 1000 kg transformer is entirely different matter, because handling a single unit of 1000 kilogram and handling a 100 kilograms unit is much easier than the 1000 kg. So as I said earlier also, because the conventional transformer has no power flow control, no power factor control, this transformer, because of its inherent power electronics that it has, it will offer power factor control, it will offer power factor control also. And then another important thing is fault isolation. Now the conventional transformers do not have their own isolation capability. They are dependent on the protection system such as relays and breakers. So they will also isolate the system from the fault. But here, because you have power electronics, you have power converter devices, these devices can be these devices can be used to control. They can be used to sense the fault and then take corrective measures, similar to the relay and circuit breaker. So these converters can provide a backup of, it's not backup, but it's a primary protection, because then the breakers and relays will become secondary protection. They will come into play later on. Before that, these power converters can isolate the system. Now the reactive power compensation, which is required with large loads where you have a low power factor, that is also additional investment. In this case of solid state transformer, you can provide this compensation through control of these power converters. So the additional reactive power compensation that we need to, compensators that we need to install when the power factor is poor, that thing is also, not required. So solid state transformer looks as a complete package. It's a complete package comprising of, transformer or voltage change system plus fault isolation, reactive power compensation, power factor control, power control, and the other one is better voltage regulation. You can also, the regulation, you don't need to tap changing system. You can regulate the voltage again through these power converters. So the output voltage regulation, frequency regulation, power compensation, fault isolation, power factor control, all these features can be combined into the single system. And these, when these transformers are installed in a substation, they will provide an easy way of renewable integration, because this transformer will also have a DC port, both sometimes high voltage DC port, sometimes low voltage DC port, or sometimes both of them. And renewable energy sources can be connected to these transformers directly. So the renewable energy source which requires converter of its own, that converter would also be additional converter will not be required. You can directly connect it to the grid through solid state transformer. So we can see that solid state transformer appears as a very sound and very attractive solution. But if that is the case, then why solid state transformer is not becoming so popular? That is the question. That means there are, many challenges in the solid state transformer. And one of the most important challenges that of efficiency. Because if you provide any solution, that solution should have, should be technologically advanced. That is one thing. But technologically advanced solution should also be cost effective, and should be efficient also. So efficiency of solid state transformer is not comparable as things stand today. It is not comparable with the conventional core type transformer. You can see here the power rating versus efficiency. The power rating, we all know that as the power rating goes up, efficiency of transformer will go up. That is something which is not questionable. So the distribution transformer efficiency goes up as the kV rating goes up. Similarly, solid state transformer power rate, this efficiency will also go up with this. What we see in this diagram is that even if we are targeting a 50 kVA transformer, the gap in efficiency is very large. It is about 98% in the conventional transformer, and it is 82% in this case. So the gap of efficiency is 16%. That large gap of efficiency will act as a deterrent in its adoption. So core type transformer efficiency is one thing. Then the traditional core type transformer offers longer life also. This transformer is a highly inexpensive, very simple system. There are windings, there is a core. You don't have much anything more than that. So the system is very simple, and it will also have because it's simple, so it will have longer life. Whereas this transformer, solid state transformer, now as we can see in this slide, we are creating a lot of power electronic system. And this will make its reliability low, and it is still, something which is under research stage. Large scale adoption is not yet there. So we need long-term testing and research to make this transformer viable for real world applications. So as I said that the cost of SST is much higher than conventional transformer, you can see here. Now as the kV rating goes up, the cost will also go up, and the gap between the cost of solid state transformer and conventional transformer, it grows up with the rating. So on the contrary, someone may think that as the power rating of solid state transformer is increased, the gap should reduce, but this gap is increasing. So this is also a real problem. So the efficiency and the cost. Now, a 100 kV SST cost nearly 5 times the conventional transformer. So what is the advantage? The advantage of size, advantage of weight, advantage of control, advantage of compensation, advantage of voltage regulation. All those things are there, but they are offset by two things. One is the efficiency, as we discussed in the last slide, and other is the cost. So if the cost is 5 times, how will you sell these advantages? These advantages can be sold in the market only if the cost becomes comparable. I don't say that cost of solid state transformer should come below the conventional low frequency transformer. But what I am convinced is that this cost should not be 20-30% more than the conventional transformer. That can be, that 30-40% of the higher cost can be justified with the advantage that it is bringing. But if the cost is 5 times, then no one will accept that. Then the other thing is that design of electrical installation for high frequency transformer is challenging due to compactness and high frequency operation. So the transformer is, you make it compact. So when you are compacting the transformer, making it compact, it is, the area available for cooling and, heat dissipation is also reducing. So that creates more challenges. And the insulation failure can also be triggered because of higher electrical stresses due to high frequency pulse width modulation waveforms. Now, as I said earlier, that this transformer, solid state transformer, will come with power electronics converters. That means these converters will need pulse width modulations, and these pulse width modulations will cause, high voltage stresses across the insulation also. So that those stresses can cause failure of insulation. Now, with this, the things as things stand today, we see that there are lots of advantages that solid state transformer has, but these advantages are also offset by the disadvantage, which is in the form of, reliability, efficiency, and then possibility of installation failure and the things that we saw in the previous slide. So installation failure, installation problem, design problem, then the cost and efficiency. But what is going to help this whole development is the arrival of SiC devices. This is a newer device which has now, which is becoming popular, which is getting into the market. So this is silicon carbide devices. What we are using is silicon devices. IGBT and MOSFETs, all those conventional devices are silicon devices. Silicon carbide devices offer another possibility of making the solid state transformer a reality. So, and the other thing is using modular topologies, the modular structure. So using modular topologies with commercial SI-based power devices, we can use complex, we will require complex control, and the issue of minimizing volume and weight would suffer. With use of wide band gap SiC devices, the converter topologies become simpler, and these can they can achieve higher efficiencies. So one of the major disadvantage of this lower efficiency can be mitigated by using SiC devices. And these devices are capable of operating at a very high voltages, very high currents, and very high frequencies. So this will the high frequency, high voltages, high currents, and the smaller size. So the overall converter size will go down. So the SiC devices, the lot of developments in SiC devices are required in the case of power in this SST also. So they can help it. We can, how can we justify this? You can see that the devices, this is a MOSFET. We'll see this through a power devices. The power output versus frequency, switching frequency. We know that MOSFET can operate at very high frequencies, but their power rating is low. So this is, up to tens of kilowatt. But if you have to go to hundreds of kilowatt, then it is IGBT. And then IGBT cannot operate at hundreds of kilohertz. Their switching frequencies are limited to 10, 20 or 30 kilohertz. Similarly, you have SiC device now. If you see this device, what it is capable of is operating at very high frequency. Instead of the limit of 10 kilohertz or 20 kilohertz is no more there in this device. It operated hundreds of kilohertz. And it can also supply high power. You can see power is now in going up to megawatt range. So this is this is an opportunity to use a device capable of operating at high frequency and also producing or also handling very large power. GaN devices are also there, which have got a further capability of very high, further high frequencies, but these devices will find application in small power rating only, because power rating is too small for, it is only, up to few kilowatt, even not even tens of kilowatt. How these devices are, SiC devices are making it possible to operate them at very high frequency. The reason is that if you see this diagram now, switching loss comparison, the turn on and turn off loss, there are two losses in the device which limit the switching frequency. One is turn on loss, other is turn off loss. Now, inherent feature of SiC MOSFET is that its turn-on loss is nearly 50%, half of Si device. So silicon device, if you compare the silicon carbide MOSFET with silicon device, then the turn-on loss is straight away 50%. And turn-off losses further reduced. You can see it is reduced by a factor of 87%. So this is a huge, benefit. And if we can operate these devices in a zero voltage switching kind of scheme, then this 50% or 49% of the drop, so 50% of the on state loss can be further made zero. And if you can make it zero, then you are left with 13% loss. So 13% loss, straight away you can increase your frequency by, if you say 100 divided by 13, say by a factor of about 7 to 8 times. So employing high voltage SiC devices, SST can offer a simple converter architecture. And what you can do is 15 kV or 10 kV SiC device. SST will only need 2 or 3 levels. Now, what we are doing in the conventional IGBTs, SI-based IGBTs, we are actually increasing the capacity by using multi-level systems. So you do not need that thing here, because the voltage and the levels are increased, and these devices can operate. Voltage level is increased, voltage of handling capability of device is increased, and these devices can operate at very high frequency. So there is no need of multi-level operation. Multi-level operation itself has its own disadvantages. You can see here a 6.5 kg kilovolt IGBT, a 2-level converter based SST can only interface of this much voltage, 2.4 kilovolt. Because IGBT, you cannot, whatever is the power electronics device, if it is 6.5 kilovolt, you cannot apply the same voltage to these devices. You need a factor of safety also. So that reduction comes to nearly 2.4 kilovolt. Whereas with a 15 kilovolt, 10 or 10 kilovolt SiC device, the SST only needs 2 or 3 levels to sustain the distribution voltage. That means 11 kV. You can directly use these devices for 11 kV with 2/3 kV 3-level system. So SiC MOSFET can significantly minimize the losses, especially the turn-off losses by itself. So this diagram, this table shows that how much is the RMS voltage and switching voltage rating. 2-level, 3-level, and then what would be the RMS applied voltage. And as it goes up, this will also go up. So the next thing is, why do we have to this new device, SiC device, which has come into the market? What are its characteristics? Now you can see the size of device. First, this is IGBT, conventional IGBT, and this is SiC-based MOSFET. The size is, everything is nearly half or even less than half, because you can see the height is 1.3, so this is 4.5, so this is at least 3 times lesser. This is nearly half, 7 to 4, and this is also not half, but nearly half. So you can easily say that overall volume would be nearly 1/3 or so, or even less than that. So you can see here the volume is 32 multiplied by 1.3. So that would become 32 plus 0.3 of this would be 10. So 42 cubic centimeter. Here it is 14 into 7, 98. 98 into 4.5, that means 100 into 4, 400. 400 is becoming, with this device, the volume of 400 centimeters cube is becoming only 42. That is almost a factor of 1/10. So the voltage rating is increased. You can see the voltage rating is increased by a factor of 2. So the power handling capability of this device and this device is more or less same. Because you can see 1.15 multiplied by 10. So that is 150. And here also this is 150, nearly 150. But the volume is 1/10th only. So these devices can this converter system will have a very small size. So SiC has a larger energy band gap, which makes it capable of operating at higher temperature also. Because junction is, the energy band gap is large, so junction can operate at high temperature. So this is not only a reduced side, but this can also operate at a high temperature. So 10 times larger breakdown electric field enables the SiC device to have much higher blocking voltage. The size and weight of SiC power device can be reduced significantly. Can I have a break of 5 minutes? Then I'll start again. Hello? Just complete it. Hello?
Hello, sir. Sir, yes, sir. Sure, sir.
Okay, I'll have a 5 minutes break because it
Sure,
is,
sir.
continuous talking.
Sure.
So
Sure,
then
sure,
I'll
sir.
continue.
Sure, sir. Thank you, sir. So, dear participants, please wait for 5 minutes. Sir will be coming back. Thank you.
Hello. So,
Yes, sir.
yeah,
Sir.
I'm starting it again. Can you see my slides?
Yes, sir. Visible, sir.
So now the next question is, what should be the topology or architecture of solid state transformer? Should be, how should we go about this? For example, the primary, issue is conversion of this power frequency voltage of certain value to a power frequency voltage of certain same frequency but different voltage. So if it's possible to convert this AC directly into a AC of 50 Hz with a solid state, with a high frequency transformer link, it would be a single stage AC to AC SST. That means, here this is low frequency or power frequency input is converted into high frequency, and then that high frequency is applied to the transformer, and next stage would convert this to AC to power frequency. This is a single stage AC-AC SST, solid state transformer. The other possibility is to have two stages. The first is convert this input to a DC supply. So this becomes high voltage DC link. And this DC link will be now utilized to convert or to will be applied to the high frequency transformer. That means the input, this DC will be used as a input to this transformer, and that would be converted into high frequency AC supply, and the output would be, from that will tap 50 Hertz or convert it back to 50 Hertz supply. So this has no DC link. This has AC only, input AC, high frequency AC, and output AC. This has got a high frequency, intermediate high voltage DC link, and then you have input AC and output AC. Intermediate, there is a high frequency AC. The third option is again a two-stage, but the DC link is now a low voltage DC link. That means this AC, power frequency AC, is applied to the high frequency transformer by converting it into high frequency signal, and then stepping it down, and then rectifying it to get a low frequency, low voltage DC link, and then change it to AC, 50 Hertz AC. So this is a direct AC to AC, first one. The second one is two-stage SST with high voltage DC link. Third one is two-stage SST with low voltage DC link. And the fourth one is a system where we have both high voltage DC link and low voltage DC link. That means the first convert this AC into DC, and then this becomes a high voltage DC link. This is now used to charge the high frequency transformer, and this high frequency transformer output is converted into DC. So there's a transformation here, so it becomes low voltage DC link, and finally this low voltage DC is converted into low voltage AC. So the next question would be which architecture or which topology to use. Use this one, or third or fourth. We will have to see the application. In case there is no application of DC supply, there is no DC load or there is no DC input, then this is good. In case there is a DC requirement of either generating station, DC generating station, or DC load of high voltage rating, this would be good. And if it's a low voltage DC link, this would be good. This will be the best option. And if you want both, integrate both high voltage and low voltage DC, this would be the best architecture. But we must be mindful that all these architectures come with a lot of converters, and inside this, each one of them there would be converters. And as we move from first to last stage, the number of converters will go up, and this increased number of converters will increase the cost, because every converter will have power electronics converter will add to the cost. It will also reduce the reliability, and it will also reduce the efficiency, because when you have more number of converters, more losses and lower efficiency. So the real issue would be a trade-off or the situation-based selection. So this first one is a single stage where direct AC to AC conversion there. It has a high efficiency and high power density, but it has got a limited functions. And the two-stage means B and C, where we have one DC link either on HV or LV side. So this, when you have a DC link, you are essentially using electrolytic capacitors, and that will make it bulky. But at the same time, integration of renewable energy sources is possible. The third one is one where we have, if you look back, this one, the third possibility, where there is active rectifier on the input side, then isolated DC-DC converter and inverter. So more functionalities here, and bulky energy storage elements are required, but you have both high voltage and low voltage DC link. Then the next issue is how to enhance the power carrying or power rating of the SST. Now, instead of using a signal system with large amount of power or large power handling capability, it would be a better to use modular structure. That is, SST, total rating of SST would be split into a rating of each cell, and then you connect these cells in certain manner. So this is the first type, input series, because input side voltage is high, So connect all the cells in series on the input side and parallel on the output side. Similarly, the other possibility is input parallel, output parallel connection. And the third possibility is input series, output series possibility. But in all these systems, we have a modular structure. That is, you plug in one module, plug in second module, plug in third module, and make, these modules will have the connections that desired, and the overall power rating or overall power will be supplied by all these modules together. So the modular structure will be like this, For example, now this case. Here there are two modules. One is, this is the first module, this is the second module. Input side, these modules are connected in series. And there are devices here, 1, 2, 3, 4. So this is a half bridge configuration. And this is another half bridge with bipolar devices, devices capable of conducting in both directions. On the output side, now what it will do is, when you apply AC here, this AC would be converted into high frequency AC through these devices, these 4 devices, and applied to respective transformer primaries. The secondary side would be a control rectifier or plus inverter. So this would be converted to 50 Hertz output, and they are in parallel. So this will convert this into the output of this would be converted to 50 Hertz output through this. So you can see this is a structure where the modularity is there, and this is a direct AC to AC conversion. On the other hand, if you see this one now, this structure, if this is a rectifier, so this is a DC link, one DC link. Similarly, this module and this module, they are connected in series on the input side. So you have 2 DC links here. And then high frequency AC through this half bridge configuration. This half bridge configuration, you do not require 2 devices because here it was AC which was applied. So you require 2 devices connected in to conduct in both directions. But here it is DC, so you don't require those. And then this is your high frequency transformer link, and this is the output. That output gets, this output side they are connected in parallel. So this is the DC output. Now to understand the application in real type of system, the real distribution system will have 3-phase AC as input and 3-phase AC as output. So this is suppose 11 kV or 10 kV input, and this is 400 volt output. How will you obtain this? So with a modular structure. Now what we can do is that each phase we have a modular structure. So this is a power module of one phase. This is a power module of second phase. And this is a power module of third phase. Each phase module has sub-modules now. This is 1, 2, 3, 4, 5. So there are 5 sub-modules in each phase here. And there are 5 transformers, high frequency transformers in this. Similarly, there are 5 modules here and 5 high frequency transformers. So 5 modules here and 5 high frequency transformers. So in total, we will have 15 modules on the input side and 15 transformers. And what we are doing is we are connecting them modules on the input side, they are connected in series so that this high voltage can be handled. And this is the DC link. This second DC link, and there are 5 high voltage DC links here, HVDC links. And then you have, this is a converter which will convert this DC into high frequency AC. And then transformer will transform this. And then this will rectify this and bring, make it DC again. So the output is DC. Similarly, output of this is DC. All of them have same type of output and they are connected in parallel here. DC output. Similarly, for second phase, you have DC outputs coming from all 5 modules and they are also connected in parallel. Third module also similarly giving you DC outputs which are connected in parallel, and all 3 DC outputs are connected in parallel to form a DC link. So this is low voltage LV DC link. And now this LV-DC link is used to, in a modular fashion again, there are AC modules now, DC to AC modules, this first module, second module, and so on. So you can use number of modules and connect them in parallel to supply the load. So you can see what advantage the modularity or modular structure is bringing. And here you can connect the number of modules, desired number of modules as per the load requirement. And here your number of modules will be more or less fixed because you have voltages, fixed voltage to handle. So you can see AC DC cell stage 150 ampere. These are devices. Frequency is this, and DC link voltage is 2.2. Similarly, other stages, and you can use high frequency. This is comparatively very high frequency as compared to the 50 Hz supply. Now, with this discussion with these 2-3 slides of discussion that we have, now we have a clear idea as to what is the real cost of SST. Now, what is the real things in the SST? Weight of SST would be not contributed, majorly it is contributed by filters, because when you have all these, converters, lot of inductors and capacitors will be required. So nearly 50% of the weight of SST is for filters. Then you have heat sinks, because you have large number of devices. They should be mounted on the heat sinks. Then DC capacitors, then semiconductor, very small weight. Transformer also comparatively small weight. Electronic also very small weight. Major is filter and cabinets. So major weight component of SST is that of filters and cabinets. Now you can see the difference in power transformer and solid state transformer. In solid state transformer, the filters and cabinets would be, majorly, major component. Similarly, the material cost. Semiconductor cost would be the major cost. Cabinets would not cost much, capacitors would not, heatsink would not, filters would cost, and transformer will cost high. So the transformer cost and transformer weight, both of them are comparatively same percentage as compared to overall thing. So we should be mindful that solid state transformer comes with lot of different perspective. It is not a simple transformer as a conventional one. Now, how do these transformers compare with each other? Now, these two diagrams, LFT and SST performance on AC-AC operation. That is input side AC, output side AC. How you can see this is, SST blue one and red one is LFT. There are three, there are, four parameters. One is weight, second is volume, third is cost, fourth is losses. If you compare, see this diagram, the cost of SST is very high as compared to LFT because it's going up to 4.5, whereas it is about 1 here or even less than 1. Losses are, if 1 here, then there are about 3 times or 2.8 times. Then weight, overall weight, if it is 1 here in this case, then this case also weight is becoming the same because of many other components. And volume is getting reduced by a small factor. But if it is this is how the technology stands today. But if it is an application of AC to DC conversion, then the things would, that means, typically battery charging, EV chargers. If you use that in EV charger, then the things are entirely different because you are giving up one stage. So the cost becomes comparable, losses are reduced, weight is dramatically reduced, and volume is also reduced. So right now, this, the EV charging products they have started adopting this. Not in large scale, but they have started adopting this. So what is the potential of SST in renewable energy? Now, renewable energy systems are a system which are based or which are developed on power electronics. So SST is a key component for realizing future grid systems. They have multi-port capabilities. They are both AC, DC, and many ports can be there. You can, you can supply both AC and DC. You can supply multiple ACs and multiple DCs. So SST can make the grid intelligent because you have a power electronics. You can deploy controllers to make them intelligent and increase reliability and safety. SST used in microgrids can be installed in remote locations. Now, when you are reducing the size, when you are reducing the weight, the transportation of transformers to the remote locations would become very easy. SST offers renewable energy system integration capability inherent. It offers reactive power support, harmonic mitigations, and better power management. But the point is, still we need to, a lot of efforts are needed to create products which can replace it because of the bottlenecks. Now, if it is to be used in microgrid, then how can it, change the whole microgrid system? Now, conventional microgrid looks like this. You have AC microgrid like this. This is a grid and transformer, step-down transformer forming the AC micro. This is the AC grid. And to this AC grid, we have AC load connected, we have DC load connected, we have distributed, distributed renewable energy generation systems in the form of solar panels. So if you connect them, want to connect to this to AC microgrid, you need DC-DC converter first and DC to AC converter. And then if it's energy storage, again you need this converter and finally DC to AC converter. And this converter will be bidirectional. So this how will this transform change if we are using a solid state transformer? With this solid state transformer, okay, with this on this diagram. Now with solid state transformer, you have a direct connection now. You can see this is the grid, this solid state transformer now. And you can directly connect these cells through one converter. The next converter is not required. You can convert this directly to this one. So in a way, these two converters are not required. So they become, this is solid state transformer can handle that. Similarly, this converter would not be required if it's a DC load. And if you have LV and HP, both of them, you can use one of them as per your requirement. And this AC load is directly supplied. Similarly, if you have DC microgrid, then in DC microgrid, you have a transformer, conventional transformer, and AC to DC converter. This is a microgrid, DC grid. And this is a DC-DC converter, this is a DC-DC converter, and directly connected DC load. And for AC load, you have DC to AC converter. How will this change if you have a solid state transformer? Now, this solid state transformer, if you, instead of this conventional transformer, if you apply solid state transformer here, then the output would be DC. The output of this would be DC. So this converter is no more required because you can use the DC link of the solid state transformer directly. So this converter is no more required. Similarly, if you want to supply AC load, this converter will not be required. You can use this one. AC output of this. So SST now has large, it is large possibilities of applications. Traction, power distribution, EV charging. In power distribution, you can have microgrid operation, smart grid operation, renewable energy integration, VAR compensation, fire fault isolation, flexibility, transmission functionalities, and hybrid things. So I think we have discussed this one. So SST enabled microgrid would look like this. This is a grid. This is a solid state transformer. We are using DC bus of this. And this is the AC bus. So you can connect AC microgrid, you can connect DC microgrid together through this one. And if you have on DC bus, you will have fuel cells, batteries, PV systems, and DC loads. And if you want to use this for renewable integration, solid state transformer for renewable integration, then you can look at this picture. This is a grid, high voltage AC grid, input stage, HVDC, high frequency transformer, low frequency DC, and output stage. Now, your distribution system, this distribution generation system, renewable generation system can be directly connected here without any, any another, you need converter for this because this voltage need to be brought to this. So DC-DC converter, no DC-AC. Similarly, here also a DC-DC converter and DC loader. On the output side, you can connect AC load here. I think, because there are a lot of many slides, but I will like to stop here because I'll take few questions if you have before I, I think, this is.
Sure, sir.
Hello. Okay.
Yeah, yes, sir. Yes, sir. Yes, sir. Thank you, sir. Thank you very much for your wonderful session, sir, on SSTs. We request participants to please, if you have any questions, we can go ahead with the sir. So, yeah, we request participants, we can interact with the chief guest. Sir, I have one question, sir. Yeah. Please go ahead. Please go ahead.
Sir, very nice session conducted by you, sir.
Okay, thank you.
Yes.
Yeah, any questions from the participants? Sir, I have a question, sir.
Yes,
so can SSTs can be effectively used in EV charging infrastructure, sir? Means when we compared with the traditional methods, traditional transformers. So if those are effectively used, then what are the design modifications that are needed, sir?
See, EV charging infrastructure will always have lot of power kilometers. Right?
Okay,
so if you
Yes,
have
sir.
a fast charging station, there will be a transformer. Hello?
Yes, sir. Yeah, yes, sir. Yes, sir.
And then you have
sir.
a number of power kilometers
Yes, sir.
from AC to DC, then DC-DC converter at least. Now,
Yes,
in case of solid state transformer, what we can do is each gun can be controlled by one solid state transformer.
Okay, sir.
So solid state transformer itself has DC output. So if you remove the last stage of solid state transformer, it becomes AC to DC. And this is what is the battery charging also doing.
Yes, sir.
So battery charging application, as I said, that this is called the immediate potential of solid state transformer can be utilized in battery charging applications, EV charging applications.
Okay, sir. Okay, sir. Thank you very much, sir. So again, it's a final call for the participants. If you have any questions, please interact with sir. If nobody have any questions, then we'll close session 1. Even if the participants are also encouraged to post their questions in the chat box.
Sir, please kindly share that PPT, then that can be useful for us.
Okay.
Thank you, sir. Thank you very much, sir, Minister.
Okay, sir. Thank you, sir. Thank you very much, sir, for your wonderful session. So we are very honored to have you, sir. So,
thank you.
Thank you, sir. In spite of your busy schedule, you have spared some time, almost 2 hours. You have engaged our participants and you have shared so many insights regarding SST. Thank you, sir. Thank you very much. And we'll be in touch with you, sir.
Okay. Okay, Allah.
Thank you,
Thank
sir.
you. Thank you.
Yeah, dear participants, so the session 2 will be started by Dr. Ravindra sir. So session will be started with less than 5 minutes. So let's stay connected to the meeting, and the next resource person will be starting the session. Thank
అది
you.
దాంట్లోనే ఉంటుంది మొత్తం అంతా ఇది తాగు అమ్మా.
Start చేయమని.
Sir, Dr. Ravindra sir, is it audible, sir?
Yeah, hello, sir.
Yeah, sir. So thank you very much for joining the session, sir. So we, on behalf of Vishnu Institute of Technology, Bhimavaram, cordially welcoming you to our online AICT Atal FDP, sir. We are very happy to have you as an expert, sir, for our FDP. So, so Dr. Ravindra sir will be presenting our session 2 on the topic solar PV fed converters for EVs using simulations. I request Professor Naveen to introduce our session 2 expert, Dr. Ravindra Garu. Over to you, Naveen sir.
Thank you, Kasim sir. Good evening, esteemed guests and participants. It's my privilege to introduce our next distinguished speaker, Dr. Dogga Ravindra Garu. Dr. Ravindra sir is an assistant professor in the Department of Electrical Engineering at Motilal Nehru Institute of Technology, Prayagraj. He completed his BTech from JNTU Kakinada and both MTech and PhD from the Indian Institute of Technology, Roorkee, where he was honored with the Excellence in Doctoral Research Award for his outstanding work in power electronics. His research primarily focuses on power electronics for electric mobility, renewable energy systems, wide band gap based power converters, solar PV systems, microgrids, and smart energy systems. Dr. Ravindra's expertise is well recognized internationally. He has delivered keynote talks and invited lectures at prestigious platforms like the University of Cambridge, World Congress of Advanced Materials, Energy Challenges Symposium, and MIC Electrical. He has also served as session chair at IEEE, scored in Malaysia in 2017, and acted as the resource person for multiple AICT, Atal, ISTE, and NIT-sponsored FDPs across India on power electronics, electric vehicles, and advanced converters. Beyond his lectures, Dr. Ravindra has been actively engaged in organizing and coordinating FDPs on advanced power converters, sustainable technologies for electric transportation, and power electronic applications. He contributes as a technical program committee member for leading IEEE international conferences worldwide and serves as a reviewer for notable journals, including IEEE Transactions on Industrial Electronics, IEEE JESTPE, IET Power Electronics, elsewhere, and Taylor and Francis publications. Currently, he serves as associate editor for the International Journal of Applied Environmental Sciences and the International Journal of Applied Power Engineering, and as an industry expert on the boards of studies at NIT Nagpur and KL University. With his extensive academic, industrial, and research experience, Dr. Ravindra sir is a distinguished authority in electric mobility, power converter design, and renewable integration, topics of immense relevance today. Please join me in warmly welcoming Dr. Ravindra sir.
Thank you, Professor Naveen, for the nice introduction. So now I request our expert, Dr. D. Ravindra sir, to kindly address the gathering. So
Yeah,
over
thank
to
you
you,
very
sir.
much, Yeah, thank you very much, sir.
Thank
And
you,
thank
sir.
you very much for warm introduction. And thank you very much for organizers for making me part in your FDP to deliver this session on solar PV fed converters for the EV using simulations. So we'll be discussing, okay, before that, let me share my screen. I hope I'm audible clearly, sir.
Yes, yes, sir. Yes, you are audible.
All right, thank
Yes,
you.
sir.
I think my screen is visible, no, sir?
Yes, sir.
All right. Okay. So, yeah, today in this session, we are going to discuss about this solar PV fed converters for EV applications. So, like using MATLAB based simulations. Okay, so first we'll see that how you can make use of the solar PV power to charge to make some kind of a charging station. Okay, so and also we can also use solar PV power. You can extract it and also you can utilize to drive our motor which is there inside electric vehicle. We'll see with the help of MATLAB simulations. Okay, so before going more into the simulation, first we'll discuss the theoretical aspects and how we can do research in this area and what are the improvements which we can make to enhance the performance in case of EV while extracting the power from the PV. Okay, first we'll discuss and then we'll go to the simulation based analysis. Right, so yeah. So if you see that like in 21st century, we countries like India, we have a lot of population growth to meet our transportation needs. Now we are moving towards this smart mobility and also we are extracting the power from the renewable energy sources. So we are trying to integrate these renewable energy sources to extract the power from renewable energy sources like solar and trying to use it to drive our the electric vehicle. So in this process, we will see that how we can integrate and the role of power electronic to integrate these renewable energy sources also to EV is very quite essential. You can see this first. We'll see that plug-in electric vehicle architecture. From this, you can see the role of power electronics is highly important, and this FDP is also like. You're focusing on like emerging trends and this advanced energy conversion technologies and applications. As you know that renewable energy and EV is like very emerging in the field of electrical domain. So now to extract the power from renewable energy and trying to integrate with your electric vehicle through power electronics. Power electronics is very essential with this in this thematic area. So you can see that whether whatever, there is a different types of charges, like you can say on board or off board. Even in on board, you see this is like based upon the power, based upon the power level, we have a level 1, so level 1 and level 2 and level 3. With whatever, like you see, whether first we'll discuss about onboard charges. You can see that there is a need, because you're having the source is that your AC. Maybe if it is a level 1, maybe in a house, or level 2, sometimes it like depending upon the power level, like depending upon the country, like countries like Germany and whatever, most of the European countries, they have at home also they have access to the three phase, like whether whatever you're having a power supply, it may, you're trying to charge your battery, right? And also some countries like Norway, there is a special grid, like two phase, and you're having renewable energy sources, then we can have a DC bus also. Whatever source you may have, like single phase or three phase or two phase, right? DC. Now the research, like even in my experience, I used to, before joining this NIT Allahabad, I was with electric vehicle company in Germany. We try to make on board their OEMs, like original equipment manufacturers, for onboard chargers. And they are OEMs for Ford and Volkswagen, uh, right, and BMW. So for them, they used to make onboard charger, and they're doing a lot of inventions in terms of like V2X capabilities, and also whatever source you may have, it may be a single phase or three phase or two phase or DC source. The same chargers would be able to capable of charging this battery. Like they are making very universal kind of a charger, and based upon whatever source you may have, just you plug your socket to the grid, and then it will identify what kind of grid it is, a single phase or two phase or three phase or DC. Accordingly, this control architecture will be reconfiguring itself to charge the battery with the help of the same power alternator. That kind of inventions are happening. That we say very smart onboard chargers, and VTX features like vehicle to everything, means vehicle to home, vehicle to load, V2L, V2Z, vehicle to grid, vehicle to vehicle, vehicle to building, like V2X, V2 everything, means we are having the energy storage element inside our electric vehicle, and the same, let us take your travel, you have taken your electric vehicle to some remote location, there you wanted to do some kind of a work, but there is no access to the grid or something like that, then the energy stored in the battery, try to utilize. Let us take, you wanted to cook the food in the remote location, then yeah, just they are keeping some, they are trying to extract the power from this, and trying to give the power to the cooker so that you can the food or something like that, electric stove or something like that. So like directly your vehicle is feeding power to the load, or vehicle to grid. Sometimes like when there is a when you're having like in some countries, they're following that very based upon peak demand and less demand. They are keeping different tariffs, right? When there is a huge demand, then they will pay you more price if you are able to sell your electrical supply to them. And means what I wanted to say is that, like when there is a power tariff is low, that time you try to charge, and also when there is a high demand from the grid side, you can sell it, so that you can do some kind of energy trading. That kind of concept also people are working, and with the help of same power technology, with the same setup, we should be able to do that. And also vehicle to vehicle, your vehicle can feed power to another vehicle without adding some additional power converter. That is our object. That kind of things we can make it. How we can make it, we'll see that. And also we wanted to extract the renewable energy, especially solar, and try to charge the battery. We'll see that. Okay, that is thing. And you see in this overall, if you wanted to have AC supply, DC supply, the same converters we wanted to utilize to extract the power and charge the battery. So in this process, like you need to have, let us take, you need to have AC to DC converter and then power factor correction circuits and then DC to DC converters. And mostly it is, if it is on board, it is like isolated DC-DC converter here, and then these since we need to have VTX, then it should be bidirectional, all these converters, and tying up with DC bus at nearly 650 volts DC. I'm taking example of Toyota Prius electric vehicle, in that they're using this 650 volts DC bus, and they're using 201.6 volts battery pack, right? To link the DC link, to integrate the DC link with battery, they're using another DC-DC bidirectional DC-DC converter, right? And then this DC link is connected with the inverter to drive the motor. Okay, and from the same DC link, and also inside a electrical vehicle, there are different types of auxiliary loads, like lighting or heating or infotainment, like entertainment, and also there is a power supply to your laptops, some mobile chargers or something like that. That kind of arrangement for that, we need to have a high gain isolated DC-DC converter. So you see that in overall, the role of power electronics is very, very, very important. Role of power electronics. EV means the role of power electronics is very much important. From this slide, you can understand. If you go ahead while integrating the renewable energy, again, it will enhance the role of power electronics. We'll see that. Okay, let us take, if you extract the power, some of the power from PV and try to use for this plug-in electrical vehicle, then again, the additional converters comes into the picture to integrate your PV with the DC bus. All right, so what they are doing is that some manufacturer, they are trying to keep also on the background. You can notice that there is a electric vehicle, and on the top chassis, like they are placing the solar PV module. Some of the power you can extract and utilize to charge the battery or something like that. Okay. So in overall, you can understand that again, the role of power electronic is further increasing, right? So you can see, okay, this is like some of the work which I said that was I was in Germany. We tried to develop very smart onboard chargers. Okay, so that is it. And now you see that. Okay, so in this you can see this is the EV, and then again, like as I said, that you wanted to have different, let us take our specific here in this session. We are talking about this solar PV power and to this electric vehicle. Then what you can do is that, like they are making some kind of renewable energy based charging station. Okay, and then that the way, maybe you're having this DC kind of a source, or you're having this commercial, like you're in some kind of a apartments where you're having three phase, or in your home you're having a single phase, trying to develop some kind of a converter which will be able to charge the batteries. Okay, this is a one kind of a thing. And another thing is that, like very ultra high fast extreme fast chargers, like through this solid state transformers, so they're using this renewable energy based integration in this path also, you can charge your electrical vehicle. Means the role of this renewable energy to charge your electrical vehicle is I'm displaying here. And like in previous case, a little bit power we have extracted from the solar and try to utilize to drive the vehicle. Right now, in this case, we are talking about a high amount of the power to extract, and then we are using. In this process, you can see, as I said, that power electronics here, again, it is further, it is increasing because the using solid state transformers are something like that, to extract the power, and then you're trying to integrate with the main grid and also to charge the chargers. In this case, again, different power converters we need to utilize it. You will see that. Okay, so and also another side of research is going on through this wireless. All right, dynamic wireless power transmission, right? So here you are keeping some kind of favor vehicle is there, and then we are trying to have this primary side of the coil and secondary side of coil you are having in the vehicle. This will be on the road or something like that. Then when the vehicle is parked, and then this through the dynamic wireless power transfer, we can able to charge the vehicle. And this also our source can be some kind of renewable energy to this primary side of the coil, like by using high frequency inverter. So again, the role of the renewable energy we are utilizing to extract the power and then to charge the battery. Okay, so various possibilities we are checking to extract the power from the solar and try to utilize to electric vehicle. That is what we are seeing in the slides so far. Okay, this is the some of the hardware implementation which I have done to this electric vehicle and utilized to extract the power from the solar. Okay, I will show you that these are the physical supercapacitor what we have done. I will show you the block. This is supercapacitors, and this is like PQ by the company, and it is like a 10 kilowatt programmable power supply. This is like programmable power supply. Okay. Okay, these I utilize like I programmed it like to act like a solar PV. Okay, so this is like programmed like a 10 kilowatt solar PV array. Okay, we have a physical supercapacitors. We have this, and this is the again Delta Electronica programmable power supply. It is I have utilized like a battery. Okay. So we have three sources like supercapacitors and batteries and PV. Okay, and from these three sources, I have extracted the power. And then if you have excess power, try to charge this is the bidirectional power supply. So storing in batteries and supercapacitor, and we are, whenever you're having high power demand in the vehicle, then we are trying to extract from these two. Okay, the complete system I have done. This is like EV motor, right? So this is like PMSM we have developed, and this PMSM is from this is the inverter module, right? This inverter we made it in a closed loop. This is the signals are coming, and we are giving to this D space, and then we are sending back to the converter. Okay, so this is like for this we have used D space. In this developed a field oriented control to control this this PMSM. This is like for loading purposes like this. Okay, so these are the converters to extract the power from. These are the like silicon carbide based means wideband gap devices are used, especially the silicon carbide to extract the power to make a DC-DC converters for three sources like PV and then battery and then supercapacitors. Okay, so and this is the complete setup. You can see whatever I have listed so far. This is the complete system. You can see. This is the solar. Okay. This is my PV source, and this is the battery. This PV source is used here. Okay, this is the battery, physical battery I used here. Sorry, programmable power supply, and this is the source of my supercapacitors. Okay, these are the converters. One is for PV, and battery, and for supercapacitor. These are the converters. All right. So this is okay, this is my inverter. I use this, and this is my motor, and then this is like this, and this entire thing I have developed here, And these control algorithm I have developed in this ESP. Okay, so this complete system I have developed and tested for EV application. This is one of the fundamental project when I was in UAE. All right, so this we will discuss. Okay, before going into further more deep, we should understand these systems. We'll try to how we have developed that hardware and then how we can make the simulation and all. We'll discuss in step by step. Okay, so before further moving, like now we are targeting about these two, like EV and PV, right? So you are designing a power alternative converter. It may be a DC-DC converter, excuse me, or DC to AC converter. How they are different, like whether it is a DC to DC for PV or DC to DC for EV. In both the cases, what DC-DC converter will do, right? It will basically, it will convert one level of DC to another level of DC, right? So it will either step up or step down depending on our requirement. It will do whether it is a PV or EV. But how they are different? We say that inverters for electric vehicle or inverters for solar, they are different. They are different in terms of their price or some other performance. Why they are different? Because the customer requirements are different. How they are different and why the designs are getting changed, we should understand. Once you understand the requirement, then you can make your hardware or prototypes or maybe commercially ready prototypes, you can make it. If you understand that to make the real-time products, you should understand first customer requirements. Let us take we are targeting a let us take you are targeting a power converters for PV. Then in case of a PV, what is the major driving factor is that because you are targeting like countries like in India, we are very much cost sensitive market we are having. Right? We are very much our customers much more than about the price, so you need to make very cost effective solutions. That is the one highest priority. And then also we need to have very good efficiency because you know that PV module efficiency is very low, like in the range of 90 to 24, something like that. If your power electric converters efficiency, if it is low, then overall system efficiency goes down. Then the power available to the load will be very less, then the things will become more difficult. That's why what we need to do. We need to have a very good, highly efficient power alternative solutions for PV. Okay, these two are our highest priorities. Like whenever you make any power alternative converters, so you should make select the topologies or components in such a way that you will be able to have very good cost and very good efficiency. Okay, so means low cost. You should be able to make your design with a low cost and highly efficient. Okay, so high efficiency. That is our priorities. And then once you have achieved these, then you should be able to focus on the reliability. Because your PV module manufacturer, they're almost giving 20 years life. Okay. Okay. So in the similar ground, you should be able to provide very good life to your customers for power alternative products as well. Okay. So then the overall PV system will be having very good life, right? So right now maybe most of the manufacturers they are giving 3 to 5 years, right? And you should be able to working on how we can increase the reliability. Okay. Once you have achieved this, then you should give priority to compactness and weight. In PV, it doesn't matter much whether it is whether lightweight or more weight, whatever it may be. You will install your converters. If you are using for residential application, then you will use it inside your home, right? Inside your home, you have a lot of space. Right, you have a lot of space to install your PV products. But whereas in case of EV, the same, if you see it, you have a very limited space inside your electric vehicle. You should be able to accommodate all your power electric converters in the limited space. That's why our priority is in case of EV is that compactness and then weight. Okay, if they are taking more space, then you will not be able to accommodate our power electric converter inside our designed mechanical design of our electric vehicle, right? So that will, if they are not fitting in within that, then how can you accommodate them? Then it is very difficult for you to sell your products to this EV segment. So you need to bother about first the compactness. Okay, once you have achieved, and then you should be able to provide a very good lightweight design, because in the lightweight design, what you need is that if your power electric converter's weight is increasing, then what will happen? The weight, dead weight of your system will increase, means your battery drains faster, right? So battery drains faster. So that is a problem. So so if lightweight, then there is a less burden on the battery not draining faster, right? So that's why you should keep a focus that your power electric converters, you need to select the topology or components in such a way that they are lightweight and very compact. Once you achieve this, then you should think about the reliability and also the efficiency. Sorry, the cost and then efficiency. This is our priority. Like this, you have to think while you are selecting the topology or component, right? In PV, this compactness and weight doesn't matter much if they are not prospered, because even it is a 10 kg or 20 kg, if they are low cost, people are much interested because they are installing the PV converters maybe on the field or maybe inside their home, where users are having a lot of space. They are much worried about the cost and efficiency in PV. Like that, with respect to other markets, also requirements are getting changed. One should understand this, and accordingly, you need to work on the selection and sizing of the components, and then selecting the component when you are making a power electronic converters. Okay. Let us talk about much more in extracting the power and driving your electrical vehicle. If you see that, okay, this is your motor load. Okay, and, one way is that since let us take, I've taken a Toyota example. In Toyota price, they are using 201.6 volts battery pack. Okay, so in coming slides, I will show you their ratings also. Anyway, so what they are trying to do is, how they are making this is, at a cell level, they are having only 1.2 volts NiMH nickel metal hydride battery cells of 1.2 volts. They're taking 168 such cells in series, and then they are able to get 201.6 volts. Okay. All right. So once you're having this, so let us take you wanted to drive a PMS motor and which needs a DC link of almost like 650 volts DC link. So since you are having 201.6 volts, one way possibility is that this 201.6 volts you can convert DC to AC of in this range, and then you can use a transformer to step up the voltage so that you will be able to get 650 volts. That is one possibility. And second possibility is that this 201.6 volts, so you can use some power line converter to step up it. And then you can get your, let us take 400 volts or something like that motor to drive it. So this is another one, all right? And if you compare these two, the pros and cons, this first solution is that you see that this 200 volts DC is converted into that range of AC, and then they are stepping up with the help of a transformer. This transformer is like a line frequency transformer, right? Because your motor is operating at electricity, something like that. Okay. So what happens is that the fundamental, whatever the fundamental motor you are using, fundamental frequency you are using, that this transformer is also at that range, right? So let us take a 250. Let us take. Means you are using a line frequency transformer. Line frequency transformers are bulky in nature, bulky, size, weight, volume, they are more, weight and volume very high. So these all are not making the solution suitable to the CD applications. That's why we don't prefer this. Although this is one possible power conversion technology, right? This is the most popularly used technology in EVs. Is that is what this architecture I have already shown you. After the battery pack, there is a DC-DC converter and then DC link. Right? So here we are using a power alternating and in case of transformer, the efficiency is also quite low compared to this power alternating converters. Power alternating converters are highly efficient compared to transformers, right? So that's why it is highly efficient solution also, and apart from compactness and lightweight and size and all. Okay, so that's why this is widely used. Apart from that, we have another method is that this, let us take you are using 201.6 volt battery pack, and you can convert in very high frequency. Let us take 100 kilohertz. At that, you have converted this DC equal voltage, and then you are using here 100 high frequency transformer. Here, let me take another color, otherwise. Okay, so here what we are trying to do is that here it is a line frequency, here it is a high frequency transformer. As you know that as frequency is going up, area requirement, volume requirement, size, weight, volume all goes down. That is the beauty of this high frequency transformer. So we are by using this high frequency transformer, we are just stepping up the voltage, and then we are having high frequency and required level of AC that we are converting to DC here. And then here we are using low frequency inverter. It's same like this. Okay. What advantage you are getting here is that you can have very high gain compared to this. Here let us take, we are saying it is a boost converter, like because we want 201.6 volts battery pack, you need to convert into 3650. Almost like you need 3.25 or something like that, the gain, right? So 3.25 is not much gain, so you can easily get with conventional boost converter, that is pretty bad. Right. And it's like you wanted to use 100 volts battery pack and you wanted to get 650, then 6.5 times gain is needed, then this converter boost converter is not your choice. You will lose a lot of performance. But theoretically, you may say that you will get infinite gain with conventional boost converter. Practically, it is limited almost like 4 to 5, depending upon the devices and a lot of other parasitic components. Right. So that's why, like when you're having wide range, wide voltage gain, then this we say that multi-stage power canal. This typically here, if you notice clearly, it is like isolated DC-DC converter, right? Isolated DC-DC. That this block diagram. we can see, understand DC to high frequency and then high frequency transform. And then this is what it is happens in all isolated DC inverters, right? So, and then inverter. Right? This could be alternative choice when you're having very high gain voltage requirement. And another side is that there is some dedicated topologies are there where you can here the requirement is that one is that stepping up and second one is inversion, right? In conventional inverter like voltage source inverter, you are much aware that in case of voltage source inverter, V naught peak is like sometimes a VDC by 2. Right. So that's why you will get, you want, let us take V naught peak, let us take at V phase, you need, let us take 230 volts, means V phase maximum, you will need a 325. Even at M is equal to 1, you need a VDC 650. Right? If you're operating at M is equal to 0.8, then you may need 650 by 0.8. That much VDC is required. But because of that, you need a high DC link. But there are dedicated topologies there in the literature where you can find the same only one power electric converter without need of any either transformer or DC-DC converter or isolated DC-DC converter. We will be able to do the both the things like stepping up as well as inversion. That is highly possible. That is also there. We'll see that. Okay, before going further and deep, you should understand the clear-cut requirements of electrical vehicle. Let us take, we'll discuss for both in case of two-wheeler and four-wheeler. First, we'll discuss in two-wheelers. Let us take, you wanted to drive your electrical vehicle on the roads where there is a maximum slope of 15 degrees or 20, 25, and then 30. I've taken 4 cases. Okay, then we are analyzing how much power is required against what is the total weight, including your vehicle weight as well as the person weight. So it is like including both. If it is a 130 cases, you would need minimum 360 watt motor. The weight is like 156 is your target weight. A person as well as the vehicle total dead weight, then it is like 423. 420 is the target, then you need a 580 watt motor. You need a 286, then you need a 740 watt motor. If again at 15 degrees maximum slope of the road, if it is 30 degrees, then you would require almost like 863 watts. All right, near to 1 kilowatt. Okay, I've taken the consideration of design of electrical vehicle with range of 75 and maximum speed is 25 kmph, right? 25 kmph I've considered because for this kind of e-cycles or something like that, it doesn't need any certification. Okay, this is the same thing with another voltage requirement. Now we have seen two-wheelers. We typically need a few kilowatts. Like I've taken very light designs. If you wanted to go for high speeds and some little bit more sloped roads, and then you would require 3 kilowatt or something like that. Right? In the range of like 1 to 5, you will be seeing case of different commercial two-wheelers. Similarly, just here I'm showing you the requirement of power converters. Means once you understand the power requirements of motor used in this electrical vehicle, then you can understand the requirement of power converters. Okay. From this slide, you can understand that there is different manufacturer like Mahindra, Renault, Mitsubishi, Volkswagen, Renault, right, Land Rover, Nissan, Hyundai, right, BYD, and then BMW, Zebeng, Mercedes-Benz, Tesla, Neo. Like that, there are different manufacturers. They make different EV models.
Sorry for interrupting, sir.
Yeah.
Sir, in the previous slide, how the theta will affect the power, sir? 15, 20, 25, and 30 degrees are there. Is that how that theta affects the power consumption?
Of course, like you want to drive a vehicle Okay, I will show you the formula. So I will.
Is that in PV is equal VI cos pi theta something?
Yes,
Is that
yes. Of course, yes.
okay?
Yeah,
So if the theta value increases,
Mhm.
so that how that power factor will be affect, sir?
No, it is not
Because
related
P
to
is equal.
power factor. Here it is related to the power requirement of the motor. Power factor is a different thing. Like power factor is from the source. We are talking at here the motor requirement, the power requirement. I am talking when you are having, if you are moving on the flat surface and you are moving on the surface like different slopes. We are talking about the power requirement. Okay,
Okay, is
so
that means the slope, sir?
yes,
Okay, so
yeah,
it's an trailing or leading like that.
yeah.
Okay,
Yeah.
sir.
Yeah. So now just from these slides you should understand when you are making a power electronic converters, what is the typical power requirements? That is what I want you to make you familiarize. You can see that in Mahindra E2O they are using there is a different variants are there like E2O plus there is different variants. In the low variant, they are using 19 kilowatt motor of induction motor, and high end variant they are using 30 kilowatt motor. And like this, you see that various manufacturers maximum we are going up to 568. In Tesla Model S, they are using in the low variant 235 kilowatt motor, and in the high end variant they are using 568. So you can understand in case of two-wheelers, it is in the few kilowatts of power motors, power requirement is there. But in case of four-wheelers, we are having a huge high power requirement is there, right? So means your power electronic converters, whatever you are targeting it, you should be uh, able to drive these motors with very lightweight and compact designs you need to make it. That is what you should understand. Okay, so this is I already told this is like more in detail about the motor requirement, battery requirements or motor specs they're using. Like you see 300 Newton meter motor and rotating speed at 10,000 almost like 10,000 RPM, 300 Newton meter motor they are using. And this is what I said, 650 volt DC link, and they're using this NIMH battery of 288 and 6.58. This is the I discussed earlier this, and these are different models. And then some variant they're using 288 and some model 214, 244 like that. Okay, so 288 volt and 6.88 or 201.6 or 6.8 batteries they are using it, right? Okay, so now once we understand the typical power ratings from where you need from few kilowatts to hundreds of kilowatt, right? We have seen almost like 565 kilowatt of power. So means if you wanted to make develop some kind of power converter, one should have a very strong and deep understanding in various fields to make a one prototype or one commercially ready power converter. So from starting from semiconductor device dies, like we are having this silicon dioxide, from that they are making silicon web, semiconductor web, silicon wafers, or maybe if you are using silicon carbide, from that they are making dies and then they are making modules. You can understand how these modules are made and how you can optimize their static and dynamic characteristics as per your requirement. You will be in your control if you make your own power modules. Okay, once you made this power module, or at least if you understand that what is their different parameters and down how they are affecting the performance at device level as well as the converter level as well as the system level, if you can understand, that will give you very good strong knowledge on the influence at system level. Maybe we are talking the EV, you can make very good power converter for EV, right? So once you're having this power modules, and then this maybe you made a IGBT or maybe MOSFET based module, they need some kind of a driver because At the end, your control algorithm will be on, okay. Your control algorithm may be there on, and the field, let us take in our company, when I worked in previous company, they used DSP processor, right? So that is like $1 cost. At the end, our entire control algorithm is developed less than 100 rupees chip. Okay, so these chips are compatible with 3.3 volts. Okay, and your power modules needs, let us take in the same charger I was talking, like they need 15 volts and minus 5 volts. During on, they need 5 volts, and during off, they need a minus 5 volts to turn on and turn off these modules. Let us take, but your controllers may be DSP or FPGA or microcontroller. So they are typically either they can provide you with 0 volts or 3.3 volts, right? Low means 0 and high means it is like 3.3. All right. If you give this kind of control signals, PWM signals to your MOSFET or IGBT, they will not be able to on, right? So what you need to do, you need to convert these things into -5 and +15, right? Or -8 +16, depending on different devices, they need different requirements. So your driver should be able to convert in. This is one of the requirement. And second requirement is that your DSP or FPGA, whatever you use it, they have a PWM pins and they have a common ground. All right. Let us take you take a 6 PWM pins, 6 PWM signals, and you're trying to give. Let us take you have a made a inverter in this one drive is there. If this one signal is giving here, and you are connecting this ground between gate and source of your device, you are giving, right. And similarly, from the second signal, second PWM signal giving to the second gate, and again you are connecting your source to this, then what will happen, this is also connected to this point, and this is also connected. I mean, these two are virtually having the same potential. This will not give you the required operation. So what should you do? You should isolate this. This should have different potential, and these two sources should be having different potential than this common ground board which are having. This is also the role of your driver. Okay, so similarly, these are the power semiconductor device. They need a high current requirements. Your microcontroller will not be able to supply that much current, so it has to your driver has to provide that. So like this, there is a various requirements which are there to drive these devices. You should be able to make a very good sophisticated driver for that. And once you made it, then means you need to place these modules and your driver, everything on the same PCB, because we wanted to have a very compact design. Compact design means a lot of, we are going for multiple layers, like 8-layer PCB, 16-layer PCB. When we are making it like the things will become more and more compact when they are making more and more, because in EV our requirement is more compactness, right? So all right, so in this process, you need to very good, sound, strong knowledge in making a very good PCBs. Okay, why? Because you are to make more compact. We are keeping multiple layers, and we are keeping your control circuit and power circuit and signal conditioning circuit, everything on the same PCB. Let us take when you are making a PCB. Let me arrange all this stuff and then we'll discuss. Okay. Okay. So when you're making on the same PCB, the power circuit and control circuit and everything, let us take for power, some tracks are carrying very high current, some tracks are carrying very low current. Control signal means when there is a two tracks are there, and these two tracks want like to carry high current, let us say. If any two current carrying conductors are displaced by dielectric medium, we say that there is a capacitance. Inherently it is coming. Right, because of this parasitic capacitance and your track is having some kind of inductance, then there will be some kind of a spikes or noise or something like that, and and that will have a very significant influence. We'll see that. So the PCB design and optimum track weights and the clearance and everything plays a very much important role. Even the bend of these tracks, everything is having significant influence. If you are very good PCB design expert, then you can make a very compact and very good sophisticated PCB at a converter level, right? So that is one of the requirement, and like one should have a very good technical understanding of making a PCB, all right. And when you are making a complete converter, in the converter you would be needing any power alternative converter. Either you need some kind of a MOSFET or IGBT or diodes, means switches or diodes or inductor or capacitor, right? Or some kind of high frequency or low transformers or something. Among all these, the weakest element is the capacitor. Right? If you make some kind of a converter, in this converter, the converter is made up with all these things, let us say. So if capacitor is the weakest, it is like somehow it is damaged. If capacitor, without capacitor, you will not get your desired output, right? So means if all are working, then it is fine. So if all are not working, then there is a problem that you will not achieve the desired thing. So you should, let us take this is having 10 years life, this is having 8 years life, this is having 7 years life, this is having only 2 years life, and transformer is having 5 years life. Let us take. Then the minimum life of your converter is only 2 years. Right? Somehow you should be able to increase this one, the weakest element. So overall converter life will increase. Right? So means that's why we need to work on the proper sizing of the capacitor, selection of the capacitor, and stresses of the capacitor and ripples, temperature rise, various things we need to focus, and then when we are making a converter. Okay, and also when we are using the switches and diode, they have a losses, right? You know that power semiconductor devices having two types of losses. One is the conduction loss, and second one is switching loss. These losses, total losses together, they what they will do, they will increase the temperature, right? Losses will not sit ideal in the system, so what they do is that they will increase the temperature. So if that this temperature, these losses will keep on with respect time, losses will be there. So temperature is keep on accumulating, and if they crosses at certain temperature, then they may kill your devices. If devices are got killed, then your converter will not be giving the required stuff. So somehow we should know how to reduce the temperature even there is a loss. So you need to cool the system. There are various types of a cooling called natural cooling, okay, or forced cooling. In forced cooling, we are having with the help of some kind of heat sinks, all right, and then maybe some kind of a fan cooling or liquid cooling, like that. There's a various ways. You should know how what is the losses and what is your target temperature rise. Bill, you wanted to operate your converter within the temperature. You should once you know that, then you can have a proper cooling mechanism. Means thermal management is very very important. So temperature means thermal management, right? So very important. Otherwise, your convective temperature goes increasing, then your your device gets killed. You will not be able to get your desired stuff. So like this, and also you, as you know that these things we are making in closed loop. So we need to know how to sense the signals, and then we need to make it very much compatible with your devices. Your controllers, maybe DSP, means your power converters are at very high power level. Let us take 1200 volts, and 30 ampere, let us take. So these power converters are operating at this much, but your DSP is only able to handle, let us take 3.3 volts. Okay. Okay. So so these signals you need to make it compatible with this DSP boards, right? So because you are operating at 1200, these devices are at a very high voltage and high current. So you need to know how to signal. You need to sense the signal and condition the signal and make it compatible with your DSP. And DSP is generating a gate signals that you are giving to drive, and drive is giving to this. And you are making it in a closed loop. So sensing is also important parameter, and then knowing how to use this, developing a control algorithms and design the controller design, and then implementation of this. You need to know embedded coding, and then like this you need to have to design one power electronic converter. You need to have expertise in all these areas which I have discussed so far. If you wanted to extract the power properly from any system, and then you wanted to utilize to maybe EV or any other load, that these are the things are very much essential. Okay, we'll move further. We'll identify some of the problems and we try to sort it out that, and then we can get some publications or something like that, right? So, okay, we'll see what are the problems in these areas, and then we'll see them with the help of maybe I will be having one more session also. In that also we will see that some of these problems in today's session, and some in that session we will be able to solve. Okay, maybe you can work with some different power and topologies, or maybe different controls, so you will be able to solve some of these problems. Okay, so let us take maybe it may be a solar or EV, or solar, or maybe renewable or EV. Our sources, let us take at cell level, they are very much very low voltage cells, right? We have. So what you need to do, let us take in case of EV, we have seen we need, let us take 650 volts DC link. Okay, so you're using 1.2 volt cells, and then you can connect several cells like 650 by 1.2. Let us take how much you will get, around maybe somewhere around you will see. Okay. So you need 650 by 1.2, you need almost like 540 cells you need to have. Okay, so you can directly take 540 cells and of 1.2 volts in 540 number, so we will achieve 650 volts. Then why we are not connecting these many cells in a series? So if you are having this 650 volt DC, then what is the need of this DC-DC converter which we have used before DC link? Directly we can use 650. Right. So, but why we are not using 650? Because compared to 650 volt system, 200 volt system is more safer, right? We are talking about a DC. There is a lot of standards they are dealing with that. We need to limit the voltage rating, and also one case we are connecting 540 in series, another case let us take 168 cells in series. In this case, each cell is having some kind of internal resistance R. In case of 540, your internal resistance is like 540 R. In this case, your internal resistance is only 168 R. Okay, even R is equal to 0.01. Let us take each cell is having 0.01. Then it is like 5.4. Even 0.001, it is like 0.54 here. It is like 0.16 here. Okay, so means 1 milli ohm internal resistance is causing this much resistance. You're carrying, let us take 30 ampere from this string, that 30 into 0.54 here. It is like almost like 900 and then 450 watt losses here. It is like 900, it is like almost like 100 watt losses here. So this is like less loss design, this one. That is what is our advantage, and also one is that efficiency because of the low internal resistance of the stack and efficiency, and we have discussed another advantage earlier, safety, and another advantage is that you are connecting 168 cells in a series in one case and another case 540. Out of 540, even one cell is gone, then this entire series pack is not having uh, any output, right? So in another case 168 one cell is gone, in that case also it is will not be able to get, but the possible probability is there here more because in case of 540 out of 540 there's a possibility is more to malfunctioning one battery cell compared to 168 case. That means that you are also losing the reliability in case of this more series connected cells design, right? So another problem is reliability. Okay, so and that's why we try to avoid as much as you can to use the series connected cells. In that case, what is the probable solution is that okay, you need to go for parallel. When you're going for the parallel, your voltage rating is limited, so you need to have very high gain converters, right? High gain converters, maybe DC to DC or in DC to DC, that can solve our problem. And also, we are because of the series connection, we are also talking about this common mode voltages, right? So in power alternating converter, when you're having a DC to AC, so there is a possibility that your common mode VNO, like generally this neutral to the this in case of let us take, we talk three-phase inverter, we are having this midpoint of input, this to neutral we have always there is some kind of a voltage, right? This common, because of this what will happen is that there is some kind of a current there flowing through the bond, like when we are talking EV, your inverter output is connected with the motor, right? There is this mechanical parts also, they carry some kind of a current because of this common mode voltages, because and also bearing current will be there, leakage currents will be there, right, through the rotor shaft and by stator and all the mechanical part, there is some kind of a current that should be that should you should limit. This common mode voltage again, it is essentially the rate of change of voltages, and then DT. We are going for high switching frequency, then DT goes down and dVdt value, overall value will increase, and also high voltage design is having more common mode. Because of the series, again, it is you are having more common mode voltages. So somehow we should decrease it further. There is a dedicated topologies are there, control schemes are there where we can get these things, right, with less common mode. And another issue is that with power decoupling, because you're having a battery is a DC, right? And let us take you're using induction motor or something like that, you have an AC. So, all right. Okay, so your input is DC. Okay, so let me take another color. Okay, so you can see that this is the VDC and IDC. Input power is like DC. Okay, even let us take you are operating at unity power factor. Let us take your inverter, you are operating in power factor. You need AC, and let us take it is like this. So what happens is that your input power is that VDC into IDC, all right, and your output power, these two should match, right? So VDC and IDC, and our output side is that what is your output power? Is that Vm sin omega t into Im sin omega t, all right? So if you multiply these two, it will be like Vm Im sin square omega t. So what is sin square omega t? Is nothing but, let me take another color. So this is nothing but Vm Im sin square omega t means 1 minus cos 2 omega t by 2, right? So
Sorry,
the
sir, your screen is not visible, sir.
sorry.
Sir, your screen is not visible, sir.
Oh, is it? Thank you for your feedback. So why it is happened? Let me share again. Hope my screen is visible now. Hello.
Yes, sir, it is visible.
Okay, thank you very much. So, all right. So now we are talking about this which we call power decoupling. Okay. So what is our, my point is here, your input is the battery. So battery typically give you, it is having, let us take voltage is DC and current is also DC, which makes your power is a DC, right? So VDC into IDC, the power is in this shape. I am calculating at the output side. Right. So even let us take let us take for best case, you are operating your voltage and currents are in phase, right? In the power factor. Okay. So let us take you're operating like this. Okay. So at unity power factor, let us take our output power is Vm sin omega t into Im sin omega t, right? So that is nothing but what it is Vm Im into sin square omega t. Okay, so if you do it, Vm Im sin square omega t is nothing but 1 minus cos 2 omega t upon t. All right, so this is nothing but Vm Im by 2 and minus Vm Im by 2 cos 2 omega t. This is your actually instantaneous power, output power is nothing but Vm Im by 2 minus Vm Im by 2 cos omega 2t. See what you understand that you, if you plot it, so what, let me take another color here. Okay, so if you take average value for this, I am taking average for this. Average means this 2 omega-t term will be 0. So it is nothing but Vm Im by 2. That is nothing but Vm by root 2 and Im by root 2. Nothing but V into I. This is your output average power is equivalent to your input average power. But if you see the instantaneous values, it is like output power is something like this, the instantaneous power. So this is your input power and this is like your output power. So sometimes your output is more, sometimes input is less. So average values are equal, but instantaneous values, they are not same. So what you need to have some kind of a buffering components. So sometimes you need to store the energy because your input is more and your output, let us take your input is less, your output is more, means you need to provide it. In this case, your output, your input is this and your output requirement is lower, so you need to store. You need to store and you need to give. Like that, you need to have some kind of energy storage elements, or like we say that a power decoupling circuit that will take care about this requirement. Okay, in case of EV, so should focus on that. And then reliability, as I said that if you have parallel converters, you need to work on the reliability, a failure of the component. Somehow you should reduce the failure rate of the components to enhance the reliability. And as I said that capacity is the one of the weakest component among all the power electronic component like LC, switches, diodes, etc. High frequency transformers, right? So somehow you should reduce the stresses on the capacitor. We have empirical relationship. There it says that if you reduce the stress of the voltage across the capacitor or ripple current flowing to the capacitor, that reduces the that will enhance the life of the capacitor. Somehow if you are enhancing the stresses by reducing the switching stresses on the capacitor, so we'll also achieve very good reliability. Okay, there is different models are there to calculate the reliability. From this you can understand that reducing the weakest component stresses, so we can enhance the reliability also, right? And also we need, in case of electrical vehicle, we have very smooth control and compact design. As I said, this is already we have decided, means for power electronic design, whatever you make, it should be very compact. And also power quality is one of the major requirement when you are giving a good quality of the power to the motor, and then the life of the motor will be good. So you need to focus on that. Okay. So these things I have already discussed with the help of previous thing. This is my input and output. That is what I have discussed. Okay. Like this.
Sir, sorry for interruption, sir.
Sorry. Hello.
Sorry for interruption, sir.
Hello.
Sir, hello, sir. Sorry for interruption.
Yeah, please.
Sir, in the previous P naught is equal to VMIM by 2 minus VMIM by 2 into cos 2 omega. The double frequencies.
Yes, that is a double line frequency component.
Why the double line frequencies exist in that?
Sorry, hello.
Sir, why the double line frequencies existed in that, sir?
Yes, that is what to match the power. We can see it here. Okay. You can see here, this is your output voltage and current requirement. Let us take at unity power factor say. If you multiply these two waveforms, you are going to, because this is a voltage, this is the current, you wanted to find out the power. And then this is my input, maybe coming from PV or battery, whatever, it will be DC. If you multiply it, you will be getting a DC. Per unit, I am doing it like the DC is 1. But you see this output side power requirement is going up to this 2 times of your in. Means sometimes you see in this area, your output side, this is your input power, your output requirement is more, and sometimes your input requirement is less. So if you mathematical also, I have shown you that the power, instantaneous power, we have calculated, it is nothing but Vm by 2 into 1 minus cos 2 omega t. This is your output power, and I should match with input power at any given time for the power balancing, right? So then what is your this thing is nothing but we have calculated Vm by 2 is nothing but V into I RMS, and 1 minus cos 2 omega t into, this is like V input is a DC, VDC into, let us take IDC of T, right? This is the battery, let us say stiff DC source. So you can see, understand that your IDC of T is nothing but VI by VDC times of 1 minus cos 2 omega t, right? Means your current is not only drawing this, this is a DC component. In addition to the DC component, your current should be able to draw additional component called VI by VDC times of cos omega. This we say it is a double line frequency component. Double line means we are having 2 times of omega t. It is not like omega t. It is a 2 times of omega t. So 2 times of a frequency, double line frequency component we say. I hope it is clear.
Yes, sir. Yes, sir. Sir, when it will be nullified, sir, when it will be tends to be 0, sir.
Yeah, it will be, it is not actually what happens is that let us take this is inverter, right? What we do, we use some kind of a capacitor. By using this capacitor, it is not active component, it is a reactive component. This 1 minus cos, if you take average value, this component will become 0, right? So it is like through this capacitors, that's why we keep some kind of electrolytic capacitor to provide this V by VI by VDC times of cos 2 omega t component of the current. We try to get it from this so that you will get a pure DC from the DC source. Okay, so otherwise you should, if you are not keeping some kind of here the current requirement is this type of current you need it. Okay, so this total current is needed at this case. So if you are not having this capacitor, this current, the entire current is should be drawn from the source. If you somehow you keep some kind of a capacitor, okay, if capacitor is providing the double line frequency component, so your DC source is should will only draw very smooth DC. It will be providing a smooth DC kind of a current, so that will enhance the life of the battery in case of EVs. That's why we typically provide a DC link capacitors. We size it such a way that this kind of a current should be drawn from this, and rest of the current DC component of current is coming from the DC source to enhance the life of the battery. That is the main idea. I hope it is clear.
Thank you, sir.
All right, thank you. So now, and another way is that some converters, what we are seeing in, let us take in VSA, voltage source inverter. What happens is that if you are turning on upper switch, your lower switch should be turned off, or else your lower switch is on means your upper switch should be turned off, right? They should be in the simulation. What we will do, we will generate one PWM pulse, and then we will give it to the NOT gate, and NOT gate the signal, and the signal will give it to the upper and lower switches. But practically it is not the case. What you need to do, because practically one switch is trying to off, and another switch is, let us take, trying to, you have stopped the pulse, let us take at this instant, but immediately at the same instant your currents will not become 0, it will take some time. Similarly, when you are giving a complement signal means it will start. So in this there is some kind of overlapping period in this, both the switches are on. That makes that short circuit, then it will draw huge amount of current and it will kill the devices and then the circuit. So what we try to do, we should have some kind of deadband between this incoming and outgoing switches. Okay, before turning on, you should ensure that you should turn off the previous upper or lower device. Okay, means outgoing switch should be turned off, and then only should be able to turn on the outgoing device. So you should have a proper deadband. We say that it is a deadband. If let us take this deadband you are providing with some maybe analog or digital way. If this is not working, entire power electronic converter will be in vain. So what we have to, but there are some highly reliable converters. Even you turn on both the switches of the same leg, nothing will happen. That kind of let us take for example, you have a Z source inverter. Let us take, you would have heard the name of Z source inverter. So if you see the structure is like this. So here you have a switching network. Okay. So even in this switching network, you have a similar kind of switch network. Even two switches are on, nothing will happen to this. Means that will enhance the more reliability. That is also another aspect. Okay. Okay, like this, these all we have covered, and let me first erase that contents and then okay. Okay, as we are reaching out to the time at 9:25, just I will quick give overview about the charges, and then we'll see the simulations in this area. Okay, so what we have discussed is that the previously we have seen several areas where you can focus to enhance the performance. All right, so if you see now we are talking about this chargers and this charger, I'm trying to power it up with the help of a PV. I will show you the simulations, okay? And also the grid is there. My battery is there. Let us take here. And this battery I wanted to charge with the help of a PV and also the grid. Okay, so this is like a grid based charger, and also I'm trying to use the renewable energy bridge because our title is to that. So I'm keeping some kind of a design such a way that you have a PV power utilized to charge, because let us take you are parking your electrical vehicle in case of, let us take some companies and all, there is a parking area there, the parking area is covered with some kind of a PV modules, and you wanted to make some kind of a system, you place the PV modules, and then also you use power electric converters, and then you make a DC bus. Similarly, you have a grid. With the help of the grid, also you make HVDC and then try to link with this DC link, and this DC link you try to utilize to charge your EV. Okay, that is the key idea. First, we'll discuss a normal charger, and then we try to integrate with the solar. Okay, so in normal, if you say that charger, what you typically needs is that AC to DC converter with the power factor correction. All right, and then we need to have some kind of isolated DC converter, because you wanted to have a proper isolation between the grid and the vehicle. All right, so vehicle battery. Okay, so that's why you need some kind of a isolated DC converter. So these two are inherently we will use it like AC to DC and the DC to DC, and you have a battery. Before this battery and DC discount, there is a filter, and also input side there is a AC side input filter for to reduce the EMI and MC. Okay, automatic compatibility. So these all converters are controlled with the help of either FPG or DSP or microphone, as we discussed earlier. So we'll see that, and we try to integrate with PV. That is our objective. Okay, so I'm not touching, since we are already away from our time. We are almost like 3 minutes left, so I will cover popular topology which we typically use is bridgeless totem pole, like we have interleaved boost, semi-bridge. Initial days, what we used to have this AC to DC, and then this PFC boost we used to have, and then semi-bridgeless topologies. They try to avoid this bridge, and then interleaved, and then this bridgeless. Okay, bridgeless totem pole is the best. This is the most widely used topology in EV chargers. Okay, because of their merits and all. Okay, so I'm not going much deep here. Just I will give you roll through the some slide which I wanted to discuss. This is the operation and all. Okay, so I will show you that we wanted to make a charger and the control I will show you. Okay, so let us take this is the, as I said, that I wanted to make a universal charger that is more compatible with whatever grid you may have, maybe 3-phase or 2-phase. This converter is configured such a way that it will be able to charge the it will be able to provide you that required DC link. Okay, for that the control scheme. Okay, we should develop it in such a way that whatever converter can be, maybe single phase converter or 3-phase or DC to DC, we should have a very adaptive in nature. Control should be there to adapt to the converter configuration, the control properly. Okay, so 1 minute. This is that control structure. I'm not much going in deep. There is various modes. As I said, that wanted to work. Whatever the objective is that whatever source you may have, there is 16 possibilities. We have to satisfy, like including, as I said, that we have either single phase grid you have, 2-phase grid you have, 3-phase DC. In 3-phase, even one line gone or 2 line gone, any one of the line gone, the charger should be able to charge. That is the customer requirement, and then it got fulfilled and perfectly. The charger is designed, and it is also given to the customer. Means in all the different cases like single phase and two phase and three phase full healthy, and in three phase one line L1 A phase gone or B phase gone, C phase gone, AB phase gone, or neutral gone, or like that there is various possible like overall 16 combinations. For all the 16 combinations, same charger is able to develop the required DC link. That is the very beautiful concept the company they have developed. Okay. So anyway, so now time is out. So I will discuss you with the simulation and then we will wind it up the session here. Since let us take, I'm using this is the solar PV module, and this is the DC-DC converter, and this is the battery. I hope you are much familiar with the MATLAB based simulation. So I like anyway, if you want to develop from the scratch, you go to the library browser, and then you are here. I'm developing the system with the help of the Simscape library, and then in the Simscape, wait a minute, I got stuck. Okay, just stuck. Give me a moment.
పదిహేడు అరవై కొట్టేయడమే కదా కొట్టలేదు.
Okay, so now you see here we need to develop. I have developed all this system in this Simscape and then electrical and then specialized power system, and then here we have our power electronic library components, and then different sources are there, right? So this from these library, specialized power system library, I have made this Simulink model, right? So by and then a basic Simulink library. Okay. Simscape, electrical, and then specialized power system library, and then Simulink library. From this, we have I have developed. This is the grade, and this is like a front end AC to DC converter and inductors, and then this is the AC to DC converter, and this is the battery DC DC converter. This is BPT, and then this is the complete control algorithm. Okay, so you can see that this is responsible for MPPT tracking. I'm sensing VPV and IPV from the PV modules. Okay, this is IPV, this is a VPV. That information I'm feeding here to MPPT. As you know that this is I have implemented P&O. We need to calculate VFK and VFK minus 1. Similarly, IFK minus 1. From that we are calculating PFK and PFK minus 1. This PFK and PF where PFK and PFK minus 1 both are equal, then we say that that is our maximum power point. So and then accordingly you will be able to produce the duty ratio to get that MPP point, right? So this is. And similarly, we have this grid side converter control is here. So you can see that I'm sensing my grid side voltage and then current. I'm controlling it on DQ frame. So I'm converting into VDVQ and then similar IDIQ, and then I'm feeding here and I'm developing this VDVQ compensate voltage, and then from that we are having the actual VDVQ and we are making a sum to that. Then we are getting a VDVQ reference and then trying to convert back via VBVC, and from that I'm developing MC, and we are providing modulation indexes, and then we are having this PW impulses, and similarly this battery side converter control is here. So once we have done these things, and then just see that I'm using let me open this. I've used PV module yet these results, as you can see that at point 2 I have reduced my irradiation, right? You can witness that I have run this simulation just before starting this. You can see that at point 2 seconds, I have reduced my radiation. Initially, it is 1000 watt per meter square, and now I reduce it to 600 watt per meter square. Accordingly, you can notice that at point 2, the power output is also in the same proportional. It is current is reduced, and since power or input radiation is got reduced, right? So, and then. Okay, this is the PV voltage and IPV, VPV and one capacitor I connected in parallel to the PV module. That current I'm showing there. Okay, this is the ICPV. Okay, these three are shown in this. Okay. If you see that this is the VPV, IPV and PPV, can see that. Okay. Since at point 2, these are the average values. So at point 2, your PV power is getting decreased. See, I have taken PV module. I've taken 14 and series PV modules and 3 in parallel, the same string. Okay, so all right. 42, and then I've taken this. You can see I've taken this. This is my VMP. See, I have taken 250 watts module. Okay. 250.
Sir, excuse me, sir. Sorry for the interruption, sir.
Yeah.
Sir,
please.
actually, sorry for the interruption, sir. But actually, the time has been exceeded, sir. To 9:30.
Okay. Thank you.
We'll
I'm just
close.
calling you.
Yeah, sure, sir. Thank you, sir.
Okay. So you can see that I'm using 250 watt modules and 14 in series of such, and then connecting them such that kind of things in 3 in parallel. So total 42, 250 into 42, 10,000, 10.5 kilowatt of PV module input. I'm taking, so you're getting 10.5 before 0.2 because my radiation is that, and then after 0.2 radiation is decreased, that's why my input power is decreased. So you can see that we are able to achieve the desired at the MPPT point, right? And I can see that this is my grade voltage and current. There I'm controlling in unity perfect. You see that perfectly. I'm getting more perfect sinusoidal voltages and anyway grid voltage sinusoidal currents is also, you see that very good quality of the power. I'm able to draw from the grid, and then I'm able to charge the battery as per my requirements. Okay, so you can see that this SOC changing. You can also see, I will show you this active and reactive powers. You can see this is the active power, third one, and fourth one is that IQ is 0, means you are operating at unity perfect. Like this, you can make a simulation model and you can complete solar powered EV charging station you can make. So with this, I will stop as you anyway time is running out, already over. So if you have any questions, feel free to discuss, and then I start my discussion here. Thank you very much.
Thank you, sir. Thank you very much for a nice session.
Thank you, sir. Yeah.
Sir, I think there are some few questions in the chat box, sir, where the participants have been posted. I will go. Sir, somewhere asked, what is the MATLAB version which you have used, sir?
I am using 2024B now. Yeah.
Okay,
This
sir.
initially I
Okay, sir.
designed in 2021 and then 22, and now I'm using 24. Yeah.
Oh, okay, sir. Okay, sir. Okay, sir. Very nice session, sir. It was very informative.
We have just given in detail version of the applications of solar PV to power electronics. So, sir, I have one question, sir.
Yeah, please.
Actually, you mentioned about the reliability and stability of with respect to reliability issue of solar PV system. Actually, do we have any validation of reliability and stability of solar PV system using simulation, sir?
Yeah, I did it, sir. But since this topic is not on reliability, that's why not done. It's not here. But yeah, we have done for complete solar PV and DC microgrid also. We calculate the reliability of each component level and the consumer level. Yes.
Okay. We can
Do it.
validate through the simulations also. Okay, sir. Okay. Thank you, sir. Dear participants, if you have any questions, please interact with our experts.
Sir, thank you, Ravindra sir. One of the best session. The most interesting thing is your slides, sir. It is create more attention to the all attendees. Very great slides, sir. Very impressive slides, which creates more attention to the users, sir.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you.
Thank you.
Any other participants? If you have any queries, please. If we don't have any queries, then we'll end the session. Thank you, Dr. Ravindra sir. Thank you very much for sparing your time for us and for the AST at FDP. So we are very happy to have you in our FDP, sir. And it's a wonderful session. And and followed with still we have 2 more sessions for you, sir, for our FDP.
Yes.
Yes, sir.
Yeah, all right, sir. Thank you very much, sir. And thank you very much for all the participants for spending your valuable time to attend this session. And thank you very much for organizers again for making me part in your FTP. Thank you very much. Yeah.
Thank you, sir. Thank you very much, sir.
Thank you. So can I leave, sir?
Yeah. Yes, sir. Okay, sir.
Thank you, sir. All right. Good night, everyone, and thank you very much. Have a great day.
Good night, sir. Good night. Dear participants, there is information that from tomorrow onward, the sessions will be starting at 6 p.m. As we have inauguration today, 30 minutes has been, extended. But from tomorrow onward, the sessions will be starting from 6 to 9. Please make a note of it. And tomorrow, means session 3, we have a session expert from ORF America. His name is Dr. Piyush Verma, a very eminent person. Tomorrow you'll get a chance to interact with him. Please be available at sharply 6 p.m. And also for session 4, Mr. C.H. Rajesh Kumar, he is the IES and Deputy Director, Central Electricity Authority, New Delhi. He's also a very famous person, and you'll get a chance to interact with him. So these are the tomorrow sessions. And again, I'm saying, so the session will be starting at 6 p.m. Please be available on that time. Thank you very much, and good night, everyone. Thank you.